Okay, all right, so ready to go. So we're gonna start the class today. In today's class, we'll be doing a new topic, starting a new topic, which is functions. But I'm gonna go through this question that we did in the last class, which is a classwork. I'm a bit disappointed with the classwork in the sense that I did not get a lot of responses from the students. Several persons did not send a solution. I want each person to send a solution, so we can go through it and see where you're going wrong before we move on. It don't make sense to move on from topic to topic, and you have gaps in your knowledge, and you have some mistakes that we don't get a chance to clear up those mistakes. So when I give you a work to do, you need to do it. When I give you a work to do and submit, you need to do it and submit it. You have to find some time to do it. These are two easy questions, right? These questions are supposed to take you half an hour to do. And I don't see where you can find half an hour to just do these two questions quickly and send them to me so I can give you some feedback as to where you're going wrong. Remember, this is an online thing now, so I have to do things a little bit differently. If you were in the classroom, how it would go is that you would not be allowed to leave the classroom until I see your work. You're not in a classroom anymore. So I cannot come and ring you on and force you on and lock the door and say you can't leave until you do your work. I'm not able to do that now. Right? That is how I did it in the classroom. When I give students classwork, if they do not come to my table and present me with the work that they did, they cannot leave the classroom. That is how the classwork sessions will go. But because we're online, I'm not able to do that. And so therefore you have to take some responsibility for yourselves now. Right? I don't have the power or that amount of power anymore to force you to do the work. Right? So you have to commit to yourself to do the work, and trust me, you cannot get success in this subject unless you do the work. Right? No matter how much you understand or feel or believe you understand something, the full understanding will come through practice and through the doing of many questions. Right? And you have to send. So a few persons send me their work and we discussed it, and I was able to say, made a mistake here, correct this, and I learned from the mistake, and they see where they're going wrong. Persons who did not do these questions, you're right, it's almost like you're right back at where we were last week Sunday. I don't know if you move forward, I don't know if you improve, I don't know if you learn it, I don't know if there's a mistake that maybe that you would have made, I would have been able to correct. Maybe you're gonna carry that mistake straight into the exam room with you in June. Whereby if you did a question, showed it to me, I would be able to say, okay, you are making this mistake, point it out to you and show you how not to make it. And you eliminate that mistake and don't carry it into the exam room. Right? So the bottom line is, when I give you work, you have to do it. Especially the classwork that you're supposed to submit to me, that I need to see the work that you are doing. Not many teachers doing online classes going to do that, in terms of private classes, Most teachers in private classes, they come and they teach and that's it. They're not going to come back outside of class hours and say, okay, send me your work, let me see and we'll discuss. I am different. I'm the kind of teacher, you can link me, send me a message, I will respond. Send me a question or whatever. So you have to use up a teacher like me. Right? Most teachers not doing that, I'm telling you. Right? When I give you work, when some teachers, when they give you work, it's not a problem to them if you don't send it, because it's less work for them. No, I want you to do the work and send it to me. So don't feel like you do me a favor if you don't do the work. I want you to do the work. You're not doing me any favors. So I need you to do the work, send me your solutions. Let me have a level of satisfaction within myself that you understand the thing. Right? One of the worst things is to move on from a topic to another topic that maybe you need to know something in this topic to be able to do the next topic and you don't know it. It means that there's going to be a gap in your knowledge. Sometimes a gap in your knowledge is going to cause it to stumble and all the other topics to come. Right? And sometimes it's something simple, You have to share the information. So when I give you a work to do, please do it. So I don't have to have this discussion any further, please. Right? When I give you a work to do, and I said do it and send me your solutions, you have to do it and send me the solution. If you're not going to do it, then I'm going to put you out of the program. And it's as simple as that, you know. Right? If I give you work to do and I don't do it, I'm just going to put you out of the program, whether you're paying or not. I'm telling you. Right? Because I'm not going to teach a set of students, they don't do the work, and then when they are not successful in the exam, they tell people that they go to Mr. Shaw's class. People who come to my class are supposed to pass and do very well. And in order for you to pass and do very well, you have to do the things that I tell you to do. Simple as that. I don't care about what other teachers telling you to do. You have to do what I tell you to do, because I know exactly that I'm telling you. I know 100% that I'm telling you the right things. I know that for a fact. So I can't go off. I can't go off and depend on what other teachers telling you. I can't say, okay, you would have learned this in another class. No, I don't care about that. Right? I want to be satisfied with myself in this program, that you learn what you need to know in this program. All right. So if you're gonna join this program, you have to go by the rules of this program, which is one of the rules is to do the work that I give it to do and send it to me. When I say send your work to me, send your work to me. When we go back in the classroom, it's gonna be that you bring your work to me so I can look at it and we can discuss it together. That is how we improve. And few persons who I would have gone through those sessions with, that's how we do one-on-one sessions. Who have gone through those sessions, I call them and I say, okay, I made a mistake here, correct this, or what have you. Right? They see the benefit of it. Right? And when you don't do it, you lose that benefit. All right? So let us not have to talk about this again, please. All right? Okay, so let me go to the classwork. All right, so this was a question, and these are all past paper questions. Right? Question 1 is clearly they give us that quadratic function there. Give us in the form of a graph, and the values P, Q, and R are not known. But looking at the graph, we can see the intersection with the x-axis, which are called the roots. One root is -½ the other root is 3. So this is one now where we need to go from the roots to the function. All right? So we're working from the roots and we're trying to get the function. So to go from the roots to the function, concept is that we're going back to the equation first. Because when you solve the equation, you would get the roots. So if we're going in the opposite direction, we can go from the roots to the equation. Then when we reach the equation is one where the expression is equal to 0. When we reach the equation, we look at the graph to see if the equation and the graph match. They correspond to each other. The equation relates to the graph. If the equation relates to the graph, then you know, okay, yes, the equation can stay as it is, and you can write the function with the same expression that is in the equation. If they don't match, most times it is that you have an equation for a smile, but the graph is a frown. And in that case, you need to change the x squared, change it so that the x squared coefficient is negative. Then you multiply by a -1. Most times what will happen is that you will get the equation with the x squared positive. That's what you'll get most times. Right? And if the graph is also a smile, it means that the x squared is supposed to be positive. And so you'll leave the equation as it is and just write the function with the same quadratic expression and don't put by the 0. And this question is also asking us for the coordinates of C, where C clearly is y-axis intercept. And that usually is your C value. In this case, is going to be your R value. R is a constant. All right, so let's go. And I'll show the two methods to do this question. We're going to do it both ways. All right. So the function that they gave us, let's look at it. Function is, the function as they give us, is y equals px squared plus qx plus r. All right, and based on the graph, we see that it smiles. It has a smile shape, and from it has a smile shape, we know that the p value, normally it would have been an a right here, but this time is a p. It doesn't matter. The p value is positive. Right, so we'll get the p value, it must be positive. We know that at the beginning. And from the graph as well, we can see the roots. So we can write that. That's all we know, the roots. The only thing we can see on this graph are the roots. So the roots are -½ and 3. -½ and 3. So okay, since we know the roots, we can write back the equation in terms of the roots. There are two ways to do it. You can write the equation in terms of the roots themselves, or you can write the equation in terms of the sum and the product of the roots. So let's say we're going to write it in terms of the roots themselves. We're going to say the equation then. The equation in terms of the roots is x minus one of the roots times x minus the other root equals 0. Every equation, every quadratic equation can be written in that form. As I've said, you would normally have a constant out here, but because you have the 0 over here, if you divide by the constant, it will be gone. So we'll just leave it off, right? There's no need to show it, so let's leave it off. So every equation can be written in that form. X minus one root times x minus the other root equals 0. And the roots are negative half and 3. So you put in the values carefully. So it becomes x minus one root is negative half. And we know that the minus minus there is positive. And the second one will be x minus the other root is 3 equals 0. All right, now one important thing is that the p, q, and r are integers. So because the p, q, and r are integers, we need to get rid of that half. Let's write it first with the plus. The minus minus is plus. So we're going to say, okay, x plus half times x minus 3 equals 0. We don't want this half because the question said p, q, and r are integers. We can get rid of this half from now. All right, you can expand it out with a half and then get rid of the half afterwards. You know, it's easier to get rid of the half from now. So to get rid of that half, because simply, why are we getting rid of the half? Because the question said over here that p, q, and r are integers. That's what it said right here. They are integers, meaning they are whole numbers, positive or negative whole numbers. All right, so what we're going to do to get rid of that half, we're going to multiply both sides of the equation by 2, but we know that we're applying the 2 to this bracket only. We're applying that 2 to this bracket only. You cannot apply the 2 to both brackets. All right, and we have repeated that multiple times and gave examples of why. So multiply both sides by 2. Then we multiply the bracket by the 2, right? You get 2x plus 1 bracket, and then you get x minus 3 still. And now this is 0 times 2 is 0. How did we get the 2x plus 1 in here? 2 times the x is 2x. And the 2 times the half is 1. All right, that is that. So now that we have those brackets, we can expand it out into the standard form. Remember, we're trying to get it out into this form up here now, standard form. So we're going to factorize it, expand it out. All right, and remember, we'll expand it out. It is the first term times the first term first. We're going to do, which is 2x squared. And the second term times the second term, 1 times negative 3 is negative 3 equals 0. Then we need a term for the middle. The term for the middle is the sum of the far product and the near product. It is a short way to do it. Looking at the short way to do it. Far product and the near product. Sum of the far product and the near product. The near product is 1x. And the far product is minus 6x. 2 times 3 is 6 minus 6x. So 1x minus 6x is negative 5x. So the middle term is just negative 5x. Because 1x minus 6x is negative 5x. So that is the equation. So we have gone from the roots to the equation right here. Now that we have gotten to the equation, we need to look and to see if the equation matches the function. Right? And it does. It's on the graph. So we can state that this equation matches the function as it appears on the graph, function graph, because it's a smile, right? And this x squared term positive, that means it's supposed to have a smile. And the y-axis intercept is negative 3. I can see that it is down here. It is down here, right? On the negative part of the y-axis, right? So that match, everything match. And since they match, we don't need to change anything. So we can say, therefore, the function is function becomes y equals 2x squared minus 5x minus 3. I don't put the 0 because you're not writing about the equation. The question said we have to determine the value of P, Q, and R. That's what the question said. So now that we have it, value of P, Q, and R, we want to do a little comparison now. Compare. So we can write the correct value for P, Q, and R. So we compare this to what they gave us. Y equal Px squared plus Qx plus R. And if we make the comparison, we can clearly see that the P is 2, the plus Q is negative 5. We don't need to put the plus, so we can take out the plus. And also the plus R is negative 3. See there? The plus R is negative 3. And the plus Q is negative 5. All right? That's it. And the P is 2. If you compare the coefficients, as simple as that. Again, we don't need to put the plus and the R. So those are the values, P, Q, and R. Answer for part 1. And the next part asks us for the coordinates for C. C is the y-axis intercept, right? C is the y-axis intercept, and we all know that the constant value is the y value on the y-axis intercept, right? So you can write that. You can write that and say, okay, for part, this is part 1, part A, the answer for part A, and part B now, y-axis intercept. So we can say C is the y-axis intercept. And it's going to be C is going to be 0R, not 0C this time, because they gave us the equation with the R. So 0R is going to be, the point C is 0, negative 3. And that's it. All right, that's doing it that way. The other method, I'm just going to write the other method up to here, up to where we get the equation, because everything else down here now would have been the same. All right, so I'm just going to work it up to that point. So let me go and do the other way. So method 2, other method. And you only need to do it one method, whichever method is you're more comfortable with, right? So remember the roots are minus half and other root is 3. And the equation, when you write it in terms of the sum of the roots, the equation is x squared minus the sum of the roots times x plus the product of the roots equals 0. And you just have to know that, right? When you can write the equation in terms of the sum and product of the roots. This is how you have to know this one up here. You write it in terms of the roots themselves. You have to know the one down here. We write it in terms of the sum and the product of the roots. So we need to calculate the sum and the product. All right, remember, we're going to put them in the equation. So the sum first. Sum of the roots, S, is going to be minus half plus 3. Minus half plus 3. So how do I add those two without having to run to a calculator? I need to convert the 3 into a fraction with the denominator as a half. So all I need to do is put it over 1 and then multiply it by 2 over 2. Right? That's all I need to do. Because if I'm adding fractions, I want all my denominators to be the same. So this becomes minus half plus 3 times 2 up here, so now is 6. So I get 6 over 2. And everybody knows that 6 over 2 is still 3. Alright? Same 3 that we had. And then it becomes, since the denominator is the same, 2, then it's 6 minus 1. 6 minus 1. And 6 minus 1 is 5. It is 5 over 2. Alright? 5 over 2 is the S value. So that value is coming right here where the S is, right there. Alright? Nice and easy. We're going for the P value now, which is the product. The product of the roots. Product of the roots, which is P. You multiply the two roots, which is minus half times 3. And when you do this, and one person made this mistake, You're multiplying by 3. You don't multiply the 3 by the numerator and the denominator. No, you don't do that. Right? Because the 3 is the same as 3 over 1. So you multiply the numerator by the numerator and the denominator by the denominator. Right? But generally speaking, if you have a fraction, if you have a number multiplied by a fraction, a over b, whatever that fraction is, you multiply the 3 by the numerator alone, it becomes 3a over b. Just know that you don't multiply by the numerator and the denominator. That's what you get. All right? I think one person made that mistake, but good. He made a mistake and he learned from it. Right? Made a mistake and he learned from it. So generally speaking, you multiply a fraction by a value, by a number, you multiply the numerator alone. All right? So that is that. That's how we cover these little things. So coming back to the question now. All right. So and that's another thing. When I'm going through the classwork and I remember the mistakes people make, I can highlight it and share it to the rest of the class. And it's a learning experience for everybody. But when you don't do the work now, we're right back at square one. So this becomes 3 times negative 1 is negative 3 over 2. So it means that negative 3 over 2 is coming here. Where the p is. What we can say is that the p is the same as plus p. So the plus p, you replace it with the negative 3 over 2. All right? Same difference. All right. So basically, we're substituting the values now. So therefore, so we can say this equation is therefore x squared minus the sum is 5 over 2. Don't forget to put the x. Don't forget to put the x. Plus the p. We said the plus p is minus 3 over 2. And that is now equal to 0. The question said the p, q, and r are integers, meaning that we don't want these fractions. So those fractions easy to turn into integers by simply multiplying through by the denominator, which is just a 2 alone. So if you multiply the equation by the 2, you get rid of the fractions, right? So you multiply the equation by 2. You multiply the equation by 2, it becomes 2x squared. I multiply this by 2, minus 5x. I multiply this by 2, the 2 cancel there. I multiply this one by 2, the 2 cancel there as well. So I get minus 3 equals 0. And then you see that it is the exact same equation that we got right here. Same equation. Right? And so the rest of it will be the same. All right? So it's a continue to end. Continue to the end. All right? As we did before the question a while ago. Same continuation. That is question 1. All right. Let us go to question 2 now. All right. So let me save this and no, let's continue on the same thing. So question 2 now. So question 2 gave us those two simultaneous equations. All right. One is a line and one is a curve, and it's helping us because it tells us that one is a line and one is a curve. So we're solving them simultaneously. So this is question 2. All right. So they gave us the line, which is 2x plus y equals 7. They say find the points of intersection of the line and the curve. So to find the points of intersection, we have to solve them simultaneously. All right, we're trying to find where they meet on a curve. And as I explained in the class, what it is that at the points of intersection, the x value on the line and the curve is the same, and the y value on the line and the curve is the same. Right? So whatever this line said the y equal to, so make y the subject of the line, for example. So y equals 2x minus 7. Or get, no, sorry, not 2x minus 7. 7 minus 2x. 7 minus 2x. So carry this 2x over and subtract it. All right, this is the line equation. So the line is saying y equals this. All right, so it means that on the curve at that point of intersection, y is equal to this on the curve as well. 7 minus 2x, as simple as that, because at the point of intersection, whatever y is equal to on the line, y is equal to the same thing on the curve. And this is the curve now. The curve is x squared minus xy equals 6. This is the curve. We're trying to find a point of intersection. And we know that the line and the curve are the same value. So at the point of intersection, the line is saying y equals that. And so the curve, the y and the curve is the same value. So it means that we can take this and replace the y and the curve there because they are the same value at the point of intersection. Simple as that. And what we are doing, we are eliminating one of the variables. So the equation now will tell us what the x values are at the points where the line and the curve meet. Right? It becomes an equation, a quadratic equation in this case. All right. So when we substitute, let's tell the examiner, we're substituting the line equation into the curve equation. We're substituting for the y value because we want only one variable to work with. We want to form an equation with only one of the unknowns. Right? Because if you form an equation with one unknown, it can be solved. The equation has two unknowns in it, you can't solve it. Right? So we're forming an equation with one unknown. So we'll substitute the line equation into the curve equation for y. I will get x squared minus x bracket, where the y is now put 7 minus 2x. And that is equal to 6. All right, so I made that substitution. Now look here. When you see these negatives, you're going to do an operation with those negatives. You have to be careful. That's where a lot of people make mistakes. You have to be careful when you're working with negatives. So once you see those negatives, you know you start to check yourself a little bit more. Be careful because most mistakes are made with the negatives. All right, so already know. We're going to expand this bracket, but remember that is negative x you're using. Negative x you're using to expand the bracket, not x. So this becomes x squared. The negative x times 7 is negative 7x. And the negative x times the negative 2x becomes positive 2x squared. So we get a plus 2x squared. All right, and then we can carry over the 6. Remember, we want to be equal to 0. So we can carry over the 6 right now. So we get negative 6, and so we have equal 0. And then put in the like terms together. All right, what are the like terms? X squared and 2x squared makes 3x squared. So we have 3x squared there. So we get 3x squared. The only x term now is this minus 7x. So we get minus 7x. And the only constant value is this now. So we get negative 6 equals 0. So that's a quadratic equation that we end up with. And when we solve this quadratic equation, it's going to give us those x values where the line and the curve intersect. All right, only the x values we're getting from this. So we're going to factorize it. All right, let's go through the factorization one time again. All right, so to factorize this, multiply the two in coefficient. Remember, if you can't solve it by a factorization, you drop it in the quadratic formula. Drop the a, b, and c in the quadratic formula. So it's 3 times negative 6 equals negative 18. Then you want factors of the negative 18 that add to this middle term, which is negative 7. Negative 7. Factors of negative 18 that add to negative 7. So we'll go now. So since we want factors of a negative number inside there, one factor will be positive and one factor will be negative. Give the larger factor the sign of this thing up here that you want. All right, because remember you're adding them to get that middle term. So the first two factors of 18 are 1 and 18. Give the larger one the negative, the smaller one the positive. But when you do 1 minus 18, you get minus 17. So you don't want that. So go to the next two factors of 18, which are 2 and 9. Give the larger one the negative and the smaller one the positive. But 2 minus 9 now is negative 7. So yes, you have found it. So you're going to split this negative 7x using positive 2x and negative 9x. All right, so we're going to do the splitting now because you found it. So what happens next is that the equation that is here becomes 3x squared. I'm going to put the minus 9x in front from this. And then I'm going to put the plus 2x from this. Why did I do that? Because I want to put the 9x with the 3x squared. Make it factorize a little bit nicer. And I'm going to put the 2x now with the minus 6. So these factorize a little bit nicer. All right, as simple as that. If I put the 2x in front, no problem. You get the same two factors anyway. And this equals 0. All right, and then you do a little check. Make sure that this will give you back the middle term, which it does. All right, so that if you make a mistake and put, if you make a mistake and you put plus here, so if you make a mistake and put plus here and minus here, you know that this will be plus 9x. You make a mistake. Always check to make sure that what you split the middle term into will give you back the original middle term that you had before. All right, always make sure, very important. All right, so that's it. So it is correct. So you do highest common factor in the first two terms, which is 3x. You factorize the 3x, and then you're going to get x minus 3. And this is a point that is very important again. If I have x minus 3 in this bracket, I must have the exact same thing in this bracket, x minus 3 first. Right? That's why we do the splitting of the middle term the way we do it, because we want the two same things to end up in the bracket. So you write back that first. You cannot put something different in the bracket. It has to be the exact same thing. Everything important. And then you look and say, okay, if the first value here is a x, what did I factorize out of the plus 2x? It must be a plus 2. Or what you can do is say you divide the plus 2x by the x that you end up in here. You see that the plus 2 go outside. Right? If you're not sure, you can look at the values as well. If I divide the minus 6x by the minus 3x, I get plus 2. Right? And then out here now, I'm not just gonna put a 2. It has to be a plus value or a minus value, one out of them. You can't just put 2 alone. So I'm putting a plus 2. Somebody did this. Somebody put nothing at all, and when them write them bracket, them write 3x minus 2 and gave it away just like that. Them write this. Simple, because they never put nothing there, so them put the wrong thing in the bracket, right? So you have to put what is supposed to be there in the bracket. Everything important, right? So it has to be plus something or minus something, because that is telling you what will be in the bracket, whether a plus or minus. And when you reach right here, do a little check. The plus 2 times the x, give me the plus 2x, right? And the plus 2 times the minus 3, give me the minus 6. So I'm going to look at expansion and check it back. So I see that it is correct. I know the factorize good. As you work, you do these little checks just to make sure you're on the right track. You don't reach the end and you have a mistake. Do your little checks as you go. Right? That way, some persons in it, they do little checks, they might necessarily make a mistake, and stop and correct it, But then they do little checks, they make go right through the mistake till them reach the end and you correct everything over. Do your little checks along the way. These little checks just to make sure. Right? Then it's 3x plus 2 times the common factor of x minus 3. Alright? So see here now it becomes 3x plus 2 times the common factor of x minus 3 equals 0. Remember, how we're doing it right here now, is finding the 2x values where the line and the curve meet. Don't forget what we're doing. Alright? So we're using a quadratic equation to find those x values. Now remember, if this times this equals 0, concept is that if the product of those, because this means multiplying, two brackets side by side means multiplying. If that first bracket times the second bracket equals 0, then either the expression in the first bracket, equals 0. Hold on a second. Either the expression in the first bracket equals 0 or the expression in the second bracket equals 0. One of them equals 0, one or both of them equals 0. Alright? Either the first bracket in the expression equals 0 or the second in the expression equals 0. Right? So you go now. That's alright. If the first one equals 0, just imagine if this equals 0. They would carry the 2 over the 0 and become negative 2, and they would divide the 3 under the negative 2. So I'm not going to show that additional step. You must can imagine that. Right? You must can imagine that. I'm not going to teach you like your babies. So it's going to become x equals negative 2 over 3. That's what we get from this, if this equals 0. And then if this one equals 0, to get the x, you just move the 3 alone over the equal sign and become positive 3. And so the other one is x equals 3. So 2 points where the line and the curve meet, where the y value is the same, right? X is equal to negative 2/3 at one of the point, and x is equal to 3 at the other point, where the line and the curve meet. Remember, it's question 2 we're doing now, right? So what happens now? You want to find the y value to go with this one, and you want the y value to go with that one, because you're finding coordinates. The question says coordinates. It never says x coordinate alone. It says coordinates. So I need the y values. So I'm going to use the equation up here with the line. The line said that the y value equals 7 minus 2x. To find what my y values are at those 2 points, right? So I'm going to say it to the examiner. I'm going to substitute into the line equation to find the y values, which is y equals 7 minus 2x. At the point, firstly, at the point where x equals negative 2/3, the y value at that point is 7 minus 2 times negative 2/3. All right? Everybody can hear me? Let me just do a little check. Everybody can hear me?
Yes, sir.
Anybody
Yes, sir.
All right, good. Everybody can see the screen. Now remember, when you multiply a value by a fraction out here, you only multiply the numerator. You don't multiply the numerator and the denominator. Only the numerator you multiply. Right? Because remember, this negative 2 here is same as negative 2/1. All right? So you have to multiply the numerator. I'm remembering some of the mistakes that people made. All right? So this then becomes y equals 7. Or the minus times the minus becomes a plus. So that becomes a plus 4 over the same denominator of 3. Then I want this to become a fraction with a denominator of 3. So what do I do? Easy. Easy. Let me space it out so you can see it better. And so it becomes a plus 4/3. So I'm going to turn this into a fraction. I'm going to simply multiply it by 3/3. Let's multiply this by 3/3. Simple. Right? And the same thing. 7 times 3 is 21. So y equals 21/3. That's what this becomes. 21/3 plus 4/3. And so that is 21 and 4 is 25/3. So when the x value is this, the y value is this at one of the points. So we can write that minus 2/3, 25/3 is one of the answers, one of the coordinates, one of the points of intersection. The next one is where x equals 3. So we can say at the point where x equals 3, at that point the y value is 7. I was substituting it here now for the 3 there to find what the y value is. Minus 2 times 3. 2 times 3 is 6, so that is 7 minus 6. Everybody knows that 7 minus 6 is 1. So when x is 3, the y value is 1 at the point. So that's the y value. So the other point is where x equals 3. Sorry. Is where x equals 3 and y equals 1. That's the other point of intersection. That's that. All right. So that was the classwork, guys. Nice and easy. All right. Somebody call them. Let's pause the video a bit and take a call. All right. So just give me a second. Let's bear with me a second. Right. We're gonna do some of this work tomorrow as well. So this class for today's topic, I would normally do it in one day, but we're gonna do some of it today and some of it tomorrow. Right, that's the benefit of online class. We have the additional day. All right, just pause the video. Okay, guys. So, but can you hear me now again?
Yes, sir.
All right.
Yes, sir.
Yes, sir.
So we're gonna move on to the topic that we're doing today. I'm gonna move on to the topic that we're doing today, which is hold on, let me set it up. Which is functions. We're doing functions today. All right. So let's go. All right. I just want to leave a little section right here so I can make a notes if I have to on the right side. All right. All right. So the topic for today, we're doing relations and functions, right? A very easy topic. Usually comes in section 1. Sometimes you can get questions in section 2, which requires a little bit more work, but it's a very nice and easy topic to do. All right. I think we're gonna do maybe about half of it today, maybe 3/4 of it today, and then tomorrow we'll do the next quarter and practice some questions, and then Wednesday is gonna be a classwork day. Then we're gonna have another functions class next week Sunday, which we'll call maybe functions 2, right? So next week we'll do some of the functions questions. I'll cover the function, the portion of the functions that they don't set very often in CXC. All right. So today and tomorrow is to cover what they normally say, the basics. Let's call it the basics. And then next week now is more application questions, application of functions. You know, so we're doing relations and functions, but we're gonna be mostly focusing on functions. Right? But we have to start with understanding relations first. All right. So let's go. All right, so what's a relation? A relation is defined as a set of ordered pairs that obey a particular rule. There's a set of ordered pairs that obey a particular rule. So the pairs basically obey the same rule, or they are related in the same way. The pairs are related in the same way. So in this example, that is a set. We know it's a set because we can see the curly brackets here. So we know it's a set. Right, that's what you normally represent a set. And these are the ordered pairs right here. All right, these are your ordered pairs. And the idea is that the -2 and the -1 are related in the exactly same way that the -1 and the 2 here is related, in exactly the same way that the 0 and the 5 is related, in exactly the same way that the 1 and the 8 is related, in exactly the same way that the 2 and the 11 is related. And it's maths we're doing, so it's usually related by some mathematical formula, some mathematical relationship we're talking about. All right, they can apply it to other things like sports or you know, people buying stuff. They can relate it to anything, right? But in the real world, but for the maths, we mostly try to use numbers to teach a concept. But you know, we can have questions that show other relations, show it in other ways. You will more than likely see some of those when you start doing maths at the add maths level or the pure maths level. We're actually doing functions questions with no numbers at all. All right, talking about sports and games and you know, there's different things, but it's still relations. All right. All right. So the set of the first elements in the ordered pairs is called the domain. So the set of the first elements. So if you take out the first elements in the pairs and put them in a set by themselves, you're basically forming a domain set, a set of domain values, which is usually represented by the X. So basically, this is your domain. Based on that set of ordered pairs that I have there as in the example, the domain, which are the X values, will be -2, -1, 0, 1, and 2. Right? So it will be -2, -1, 0, 1, and 2. Those are the first values, are the X values. That is your domain. All right. And then the set of second values is called the range, but the proper name for the set of second values, so you want to make a note for me, is really CoDomain, because CoDomain and range, they really have a slightly different definition. There's a little nuance. At CSEC, they won't get into the difference between they won't get into the whole idea or the details of what is the difference between CoDomain and range, right? But the proper name for the set of second values is really your CoDomain. In this case, they're going to be a range because there are values that are actually mapped onto, right? But you know, the CoDomain, sometimes you'll see CoDomain instead of range. So the range are the actual Y values that are there in the ordered pairs. CoDomain is basically the set of Y values that could have been in the ordered pairs. But don't worry too much about the definition. But for now, this will be a range. For this set of ordered pairs, that will be a range. Those are your actual y values, right? So we're talking about the -1, the 2, the 5, the 8, and the 11. Those are the values now that go to make up your range. All right? That's a codomain and your range. All right, so we're going to an example now. So in the example above, the rule which governs the relations that we just looked at is that x is mapped onto 3x plus 5. X is mapped onto 3x plus 5. That's what this thing means. X is mapped onto 3x plus 5. It means that if a domain value is x, the range value is going to be 3x plus 5. That's what that means. All right. And how that, another way of expressing it is to say y value equals 3x plus 5. So it comes back to like a linear equation, right? So the relation can also be shown on a mapping diagram or on a graph. But let me give you one example first. So we are saying that the relation is that x maps onto 3x plus 5. So we'll just look at a couple of the values and show why that is so, right? So let me clear this off before we move on. All right. So so if you look at one of the ordered pairs, it was -2 mapped onto -1. That's the first pair. Because remember the point was -2, -1. How that works is that the -2, just to prove it, will map onto 3 times -2 plus 5. And this works out to -1. So you can see that because this is -6 plus 5. So that's how we get the -1. And if you try the other pair, which is a -1, the -1, that is the second pair, the -1 would map onto 3 times -1 plus 5. But this is -3. -3 plus 5 is 2. So it's that -1 is mapping onto 2. You can see that over there. And if you look at the 0 maps onto 3 times the 0 plus 5, which is a 5. That's why the point 0, 5 there. And the next one, the 1, map onto 3 times 1 plus 5, right? We're looking at this one now on the right side, that one, on the left side, sorry. And that works out to be 8. So that's why the 1 map onto 8. And then the last pair is the 2 map onto 3 times 2, which is 6 plus 5. That is 6 plus 5 is 11. So 2 maps onto 11. That's why I get that last pair, 2, 11. All right, so those are your pairs, and that's how the calculation will go. All right, so moving back to this one now, that's a relation. I'm saying it can be shown on what you call a mapping diagram, or it can be shown on a graph. All right, so a relation can be shown on a mapping diagram, or it can be shown on a graph. So if we're going to show this set of ordered pairs on a mapping diagram, you basically draw two sets like that. Well, the x mapping onto 3x plus 5, that's relation. X maps onto 3x plus 5. So you draw this oval here for the domain, for the set of domain values, and draw this oval for the set of range values. All right. So that's how you do it. And then you put the values in there. So you put the domain values in the first one, and you put the range values in the second one. So those are your domain values in the first one. And then those are your range values in the second one. And then what you do, you join the corresponding values with arrows from the left, from the domain over to the range. So you draw an arrow from the -2 to the -1, because that was one pair. You draw an arrow from the -1 to the 2, that was your second pair. You draw an arrow from the 0 to the 5, that was the third pair. The fourth pair is 1 to 8. And the last pair that we have there is 2 to 11. So that will be your mapping diagram, right? And this will be a one-to-one relation because it's one value in the domain mapping to only one value in the range. So this will be a one-to-one relation, all right? Because the relation are described that way, you know, in terms of how the mapping go. So this will be a one-to-one. One value in the domain mapping to one value only in the codomain. All right. You can also, as I said, show it on a graph. So you can see what it looks like on a graph. You can see the relationship on a graph. So basically, it's just the same as plotting points on a graph. Right. So this one is pretty straightforward. Right. So this point down here is for this one, the -2, -1. right? And this point is for the negative 1, 2. Everybody can see that, negative 1, 2. Then the 0, 5 is this one up here, the 0, 5. And then the 1, 8. The 1, 8 is this one. See, 1 across, 8 up. Everybody can see that. And then the 2, 11 is this one. See it here, 2 across to the right, and then 11 up there. So those are the points, right? And then you just draw the line through them. You could leave it like that as a set of ordered pairs, you know. If you want to show the line, show what kind of relationship it have, you can draw the straight line through it. But if you leave that as your graph with those points alone, right, that will basically represent the relation that was given as a set of ordered pairs. But to show that it has a linear relation, you can actually now put a line through the points, and you see that it is linear, right? Show that it is linear, because the change is a linear change from point to point. All right. Now we'll get into function now. Now, what is a function? Function now is a relation that has a specific definition and must have certain specific conditions met for the relation to be a function. All right. And there are certain things that you can now do with functions, and there are certain things that cannot happen if something is not a function. All right. So for certain things to happen, a relation has to be a function. Like, for example, an inverse. Right? Only a one-to-one function can have an inverse. So you need to know what's a function and what is not a function. All right. So this is the definition of what a function is. You have to be able to identify a function graphically, or look at a graph and know if it's a function or not. You also have to be able to look at a mapping diagram and know if it's a function or not. I'm going to show you that just now. So a function is a relation in which each element in the domain is mapped onto one and only one element in the range. Now, what does that mean in normal term? All this means is that each of the elements in the domain must map, and when they map, they must map only one time. That's the simplest way of saying it. So this fancy statement here simply means that each of the elements in the domain must map. In other words, you can't have any free element in the domain that is not mapping. And when they map, they have to map only one time alone. In other words, no element in the domain can map twice or 3 times. They can only map one time. All right. And if you notice, the definition is only speaking about the domain. It only makes reference to the domain. So what it means is that it is the domain. It is what is happening in the domain that decides if you have a function or not. What is happening in the codomain don't matter. It is irrelevant. It is what is happening in the domain that decides. So remember now, this fancy statement here, right, that you'll see in any book, simply means that all the elements in the domain must map. And when they map, they can only map one time alone. In other words, each element in the domain must have one arrow alone coming off it. So when you look at a mapping diagram for a relation, it is a function if each of the elements in the domain have an arrow coming off it, and it has to be only one arrow coming off it. So if you have an element in the domain with no arrow coming off it, it is not a function, because each element must map. And if you have an element in the domain with 2 arrows coming off it, then it's not a function, because each element must map one time to the codomain or to the range. That's what this statement means. All right, in layman term. We're going to do some examples. So the function, so remember I spoke to you about that is the domain that decides if a function or not. So the function can only be fully defined, meaning to say what kind of function it is, only after the domain itself is defined. In other words, you have to know what is happening in the domain to know what kind of function you have, if you have a function or not, right? The definition of a range therefore depends on the domain. So what happens in the range depends on what is happening in the domain, right? So the domain, when the domain is not stated, it is assumed that it can take all real values. This statement means it can take all real values of x. That's what that statement. X is a member. There are there means real values of x. So if they don't define the domain for you and tell you what the domain is, you assume that it can take any x value, right? Any real x value. All right. So let's look at a one-to-one relation. Let's look at the type of relations now, and which ones are functions and which ones are not. So one-to-one relations are functions. All right. One-to-one relations are functions because they will satisfy the definition up here. One-to-one relations will satisfy that definition up here. All right. So the first one that we looked at is a one-to-one function. And we saw that on the mapping diagram that each element in the domain had only one arrow coming off it. And that is why it is a function. And then now they were mapping to only one element in the range. Right. And it is called a linear relation. And it's there. It was a linear relation and it was one-to-one. Because if you looked at the mapping diagram, it all there were only one arrow mapping to one element mapped to only one element. One element in the domain was mapping to only one element in the range. There was no crisscrossing or mix-up or no multiple mapping, right? It was one-to-one. And because we know the relation is a function, we can now introduce it as a function. We can now introduce it as a function. And when you introduce it as a function, you can now write it away different from this. That's when you know it's a relation. But now that you know that it's a function, you can now write it like that by putting this thing in front of it now. The function is such that, because you now know that it is a function. It's not just a relation anymore, it is now a function, right? And that now means the function of x is 3x plus 5, right? You can also write it like that. F of x equals 3x plus 5, or go back to the y equals 3x plus 5. And that's a linear function. It's not a function. All right. So these three things basically saying the same thing. Those three things mean the same thing, just written in different ways. All right. Let me continue. So let's look now at, okay, the determinant of a function is one-to-one. To determine, I'm going to do some examples later. So if you don't understand this fully that I'm going to look at now, don't worry yourself. We're going to do some examples shortly, right? To determine if a function is one-to-one, all right, on a graph. I'm talking about on a graph. We can do what we call a horizontal line test, right? So a function f is one-to-one when each element in the range is the image of only one element in the domain, meaning one element mapping to only one element. That's all it means, right? So a horizontal line test on a graph can be used to determine if a function is one-to-one. So if you have a graph and you draw a horizontal line on the graph, if you have a function graph, let me make more specific. If you have a function graph and you draw a horizontal line on that function graph and the line intersects the graph at only one point, then it means that you have the graph of a function. No, let me say it another way. Let me say it again. If you have a function graph and you draw a horizontal line on the graph and the graph intersects that function graph at only one point, it means that that graph is a graph of a one-to-one function. But the important thing is that it has to be a function graph. I'm going to explain this a little bit better. We'll do some examples later. All right. So these are two examples. This is a function graph. All right. And I'll tell you later why it's a function graph. This blue graph is a function graph. Any horizontal line I draw on this graph can only intersect it at one point. Any horizontal line I draw will intersect this graph at only one point. And so this is a one-to-one function. The next example, that graph, it is a function graph again. And I explain to you later why it's a function graph. Now this function graph, if I draw a horizontal line here, it will intersect at 3 points. Now if I draw one up here, no, it will intersect at 1 point, but this section supersedes here. So therefore, it's a many-to-one function. Many-to-one function. Let me show you what we mean by many-to-one a little bit. All right, let's look what I mean. This point means that it is one x value giving you one y value there. One x value mapping to one y value at all the points. And the one on the right, it is three different x values. Three different x values. You can call it x1, x2, and x3. Right? Three different x values giving you the same y value here. 3 different x values giving you the same y value. That is why it's many x values mapping to one y value. All right. So that is why it is many to one. But generally speaking, if a horizontal line intersect a function graph more than once, it is many to one. All right. Simple as that. All right. So let's look at a many to one relation now, which also is a function. And you'll see that once the mapping is to one, it is a function. All right. Once the mapping is to one, it is a function. So whether it's 1 to 1 or many to one, we have a function. If it is to many, once the mapping is to many, once the mapping is to many, not a function. Not a function. So once it is 1 to 1 or many to 1, you have a function. If the mapping is to many, you're not a function. It has to be one output. Think of a calculator. A calculator is like a function calculator. Right? A function calculator can only give you one answer. When you're doing the work on a calculator, a function calculator, and you press equal, you're getting only one output. Right? So a relation that can give you only one output, where the input values can give you only one output. So think of it that way. Many to one or 1 to 1. Right? It is a function. Okay, you can only get one output from the relation. All right. So let's look at this example where x is mapped onto x squared. So x values are mapped onto x squared values. So that's looking at that relation, which is a quadratic relation. All right. So we're going to use a set of ordered pairs, starting from an x value of -2 and going to x value of 2. And we're using a whole number of values. So it means that those x values will be -2, -1, 0, 1, and 2. So those will be your domain values. All right. Those would be your domain values in this example. All right. And then we're going to look at the mapping diagram from it for these pairs now. So you have the domain and you have the range. Remember, the first oval there is for your domain. The second one is for your range. So you're going to put the domain values in the first one. So them there, -2, -1, 0, 1, and 2. Now, look here now. The range values are only 3 values. So even though, for example, you have a 4 here, so, and the 4 there, so, an element can only appear in a set once. So you can't put 2 4s in the set, you know. Similarly, you have 1 here, so, and 1 here, so, as 2 range values. You can't put 1 in the set twice. You can only put an element in a set twice. An element is just an element. All right? It's a set. You cannot put an element in a set twice. All right? So even though you have 2 points with 4 twice, you can only put 4 in the set once. All right? And then now you're going to draw the mapping diagram. So you look at it, the -2, let me clear the screen. The -2 mapping to the 4. That's the first one we're looking at there. The second one is a -1 mapping to the 1 right there. The third one is that 0 maps to 0. The next one is that 1 maps to 1. And the last one is that we see the mapping come back to 1. 1 map back to 1. So 2 things mapping to 1, the -1 and the 1. And then the 2 also maps to 4. Nobody understand that? Because remember now, it's x mapping to x squared. So let's look at some examples. So -2 would map to -2 squared. That's how we get the 4. Right? That's how we get the 4. Let me write that again. Right. So the -2, get by the pen, get by the pen. I don't understand how this thing works sometimes. It's just doing its own thing. All right, erase all. All right, let's go again. It's a struggle sometimes, guys. All right. All right, so look at it now. I'm saying that the x maps to x squared. So we'll get the values. The negative 2 maps to negative 2 squared. That's how we get the 4. And the negative 1 maps to negative 1 squared. Negative 1 squared is 1. Then the 0 maps to 0 squared. 0 squared is 0. Then the 1 maps to 1 squared. 1 squared is 1. And then the 2 maps to 2 squared. And the 2 squared is 4. So that's how we get those pairs. All right? That's how we get those pairs. So nothing complicated. All right? And then so we get that mapping diagram. Then now we can also show the information on a graph by just plotting the points. All right? So see there now, we've plotted the points. Those are the points there. So this one, negative 2, 4 is this one. Negative 1, 1 is this one. This point is 0, 0. And this point is 1, 1 right here. And then this point is 2, 4. 2, 4 is right there. So those are your points. And to show the relationship, we put a graph through it like that. So if we put a horizontal line on this graph now, right, you're going to see that the horizontal line is going to intersect the graph twice, right? And you can see the mapping. So you can see the negative 2 mapping up here to the 4. You can see it. And the negative 1 mapping to the 1. And then you can see the 1 also mapping to 1. So you see that's 2 values. Let me clean the screen so you can see it. So it's 2 different values. 2 different values mapping, both of them mapping to the same y value. And here again, 2 different values mapping to the same y value. 2 different values mapping to the same 1. So that's how you get the many to 1 on a graph. And that is why if you draw a horizontal line on a graph, it will intersect the graph more than once. And so that's a many to 1. Many to 1. All right, so that's a many to 1. So in this case of the quadratic relation, 2 different elements in the domain map to the same 1 element in the range, but each element is mapping only 1 still. So let's look back at that. If you look over here, why is this a function? Because each element map, because each element is mapping over here. This map 1 time. Look at them now. Let's look at it. This one have 1 arrow alone coming off it. This one has 1 element, 1 arrow alone coming off it. This has 1 arrow alone coming off it. This has 1 arrow alone coming off it. And this has 1 arrow alone coming off it. And there are no free elements in there. That is why it is a function. But this element mapping and this element map to the same 1 element. So 2 different elements mapping to the same 1 element. And that's all you need to know. You only need it to occur once in the mapping. And that is why it is a many mapping to 1. It is a function because each element in the domain map only 1 time, but it's a many to 1 because 2 elements mapping to 1 element. All right, so that is why it is a many to 1. All right, let me continue. So that's what this is saying. All right, and then now, because we now know it's a function, the same thing again. Because we now know that the relation is a function, we can now introduce the f business. See there? We're now introducing the f thing. I say f is such that x is mapped onto x squared, because we now know it's not just x mapped onto x squared relation anymore. We now know it's a function, right? We know it's a function because it satisfies the definition of a function in that each element in the domain map only 1 time. It just happens to be that many map to 1, and so it's a many to 1 function, right? We can also write it like that now. F of x equals x squared or y equals x squared. Now that we know it's a function. All right, let's continue. Then we have one-to-many relation. And a one-to-many relation is not a function. So most times when you get a relation that is not a function in CSEC, it's going to be a one-to-many. Most times in CSEC, it's going to be a one-to-many. If you ever have a many-to-many relation, if that is possible, that also would not be a function because it is something to many. But most times only 3 relations that they'll give you. One-to-one, many-to-one, or one-to-many. The one-to-many is not a function. The one-to-many is not a function. All right, many to many would be something complicated on a graph, kind of complicated. So let's look at it. So we're looking at this relation now that x maps onto plus or minus the square root of x. I'm just using some values to make it kind of easy. What this means is that x maps onto the positive square root of x, and at the same time, x maps onto the negative square root of x. That's what it means. So it's two things x value, one x value mapping onto. One x value is mapping onto the positive square root of x, and it's also mapping onto the negative square root of x. That's what this means. And the x values we're using are the whole numbers 0 to 4. All right, we're using 0 to 4. So we're going to be using 0, 1, and 4. Just keeping it simple. All right, so we're using 0, 1, and 4. So you can see, look at the mapping. 0 would map onto positive square root of 0, which is 0. And also, it will map onto negative square root of 0, which is still 0. Then 1 would map onto the positive square root of 1, which is 1. And it will also map onto the negative square root of 1, which is negative 1. Because you're not square rooting this negative, you know. I should not have done that. I don't like to use this function. Erase. All right, come again. Come again. So we're saying the x up here is mapping onto a positive root x, and also it is mapping onto a negative root x. All right, the 0 is mapping onto, positive root 0, which is 0. And the 0 is also at the same time mapping onto positive negative root 0, which is still 0. The 1 is mapping onto positive root 1, which is 1. And the 1 is also mapping onto negative root 1, which is negative 1. All right, so that's 1 to many. The 4 is mapping onto positive root 4, which is 2. And the 4 is also mapping onto negative root 4, which is negative 2. So you see 4 mapping onto 2 and negative 2, 1 mapping onto 1 and negative 1, and 0 mapping onto 0. So that's 1 to many. All right, let's do the mapping diagram to show it. So remember, I know each value can only appear in a set 1. So the domain values will be just 0, 1, and 4. 0, 1, and 4 are your domain values. But the range values now would be 0, would be negative 2, negative 1, 0, 1, and 2. Okay, we'll put in the plus and the minus in there. So that would be your range values. Negative 2, negative 1, 0, 1, and 2. And then you do your mapping now. So 0 map onto 0, that's it. 1 map onto negative 1, and 1 also map onto 1. Then 4 map onto negative 2, and 4 also map onto 2. Right? So you can see that this is not a function, because you have this one element right here, so already having 2 arrows coming off it. 2 arrows coming off it. The rule says each element must have only 1 arrow coming off it. This also causes it not to be a function, because again, it has 2 arrows coming off it. Right? It mapping twice. So those 2 are causing that relation not to be a function, because then it would not satisfy the definition of what a function is. For the relation to be a function, when you draw the mapping diagram, each element in the domain must have only 1 mapping to the codomain or to the range. All right, let's look at it graphically now. Let's look at it graphically. So looking at it graphically, those will be the points. Those will be the points. And you can see it. That will be the graph of the points. So it will be a graph like that. All right, and now we're going to introduce what we call a vertical line test just now. All right, so you can see the mapping now. The 1 is mapping on to 1 and negative 1. So this 1 value here is mapping up here to 1, and also mapping down here to negative 1. And the 4 is mapping up here to 2, and also mapping down here to 2. So you see 1 x value is mapping on to 2 y values here and there. And on this side, one x value is mapping onto two y values, there and there. And so now we introduce the concept of the vertical line test just now. All right. So that will be the graph of that function. So let me clear it, the graph now again. All right. That is a graph. All right. You can see the one x value down here mapping to two different y values as an example. So that's one mapping to many. All right. So in this case, each element in the domain, there are elements in the domain that map twice, map to two elements in the range, right? Under that relation. And therefore, this relation is not a function. And because this relation now is not a function, we cannot talk about no f. We can't call it no f. We don't write it as no f because it is not a function. So we don't introduce the whole concept of the function on this one. We don't write no f is such that for this one because it is not a function. All right, as simple as that. And a one-to-many relation is not a function. So don't put no f is such that business on it. The f is such that is reserved for functions. All right. Now look here now. We're going to introduce now how you can test if you have a function or not. All right. I'm going to use mapping diagram. I'm going to use graph. So this should help us to understand a little bit better now. All right. So we can do what we call a vertical line test to determine if the graph of a relation is a function or not. All right. If when you draw a vertical line on a graph, it intersects the graph more than once, more than one time, it means that that now is the graph of something that is not a function. I'll put another way. If a vertical line intersects a graph only one time alone, if any vertical line on a graph can intersect the graph only one time alone, then that is the graph of a function. All right, so we have the vertical line test to test if you have a function or not. We have the horizontal line test to test what kind of function you have. All right, so one point of intersection, you have a function. More than one point of intersection, you don't have a function. More than one point of intersection is not a function. All right. So before we get into that, let's do the little test. Now remember, make a note of this for me, please. Make a note of this for me, please. All right, let me write it down here. So we're doing the vertical line test and the horizontal line test. So let's call it the V line test first. And for the V line test, you do this first. You do this first. Always do the vertical line test first. What does that tell you? It tells you if you have a function or not a function. Then second, you do the horizontal line test. Do the horizontal line test afterwards. So you do this one second. Because this one will tell you what kind of function or the type of function. If it is a function, it tells you the type of function. So make a note of this for me, please. Make a note of this for me, please. You must always do the vertical line test first on a graph. That's when you want to see if a graph is a graph of a function or not, and also what kind of function it is. Now remember, I know if you do the vertical line test and it is not a function, they can go into saying whether it's one-to-one or many-to-one. And remember, the type of function is either one-to-one, one-to-one, or many-to-one. Many-to-one. Those are your kinds of function. So, but you have to do the vertical line test first to see if it's a function or not. If it is a function, then no, the horizontal line test will tell you what kind of function it is. But if it is not a function, then you stop. You know, but I want to know what kind of function it is. I'm going to give you examples now. So watch this now. Let's go and look at some examples of something now. All right, let's look at some examples of something now. I want to show you guys something. Where is it? Here. Let me show you something. All right, so we're going to look at this one first. Let's look at the mapping diagram first and then the graph. Oh, it's still a full screen. Look a bit. All right. let's do this a little bit first. All right, guys. So, everybody with me? What we're gonna do here? We're gonna look at these mapping diagrams, right? We're mapping the domain on the left to the codomain or the range on the right. We just call it codomain this time because it's a proper name. The range are the values that are actually mapped on. Codomain is a set that you can map onto, right? So, for example, in this example right here, these are actually mapped onto, so those would form the range. This value is not mapped onto, but it is also in the set, so it forms a part of the codomain, right? So those values that I have circled would be the actual range values, all right? If you actually know those, as I'm just using dots as if they were values, like numbers, right? So what I want you to help me with now, and I want to unmute your mic, right, and tell me which of these are functions and which are not. We're going to do one at a time. And if it is not a function, you're going to tell me why. If it is a function, you're going to tell me why. So talk to me now, somebody. The first one, looking at this one. Is that a function or not a function? Is that a mapping diagram?
It's a function.
You're saying yes. All right. Anybody else? I just want to hear some answers. Anybody else?
Yes, it's a function.
Anybody else? Anybody say it's not? Anybody think it is not a function? Two persons said it is a function. Anybody think it is not a function? So everybody believe it that it is a function then. By not saying anything, I'm saying that you all believe it's a function.
Yes, sir.
All right. So let me show you now. Now remember, the rule for it to be a function is that each, now see the word each means every in this sense. Each element must map in the code, in the domain. And when it must map only one time, right? This element right here, let me use the red ink. This element right here in the domain has no mapping. Does not map. Right? It is not mapping. See that? And therefore it is not a function. Simply because that element in the domain is not mapping. The rule says you can't have no free element in the domain when I map. Every element in the domain must map. And when they map, they have to map one time alone. So that element there is causing this relation not to be a function. It's a one-to-one relation, but it is not a function. So this is a one-to-one relation. I would say the elements that map, they only map one-to-one, one-to-one. It's a one-to-one relation, but it's not a function. So this is not a function. So this causes it not to be a function. This because of this, it is not a function. Not a function. Because the rule says each element, each means every one of them, each of the elements in the domain must have a mapping. If you have an element in the domain that is not mapping, no, it's not a function. Right? I remember, you don't care about what mean the codomain, in there, It don't matter what happens over there. That is irrelevant. Right? The codomain don't determine if you have a function or not. When you do maths at a higher level, right? It will determine what kind of function you have, because you have some things what them call surjective and injective, and you have another thing what them call onto, and these things, and bijective. But you're not dealing with those things at CSEC, right? And the codomain now becomes significant, whether you have a range, whether the range and the codomain equal or they're not equal, and these things to determine what kind of function you have at the higher level. But at this level, your interest is only in the domain. So everybody understand that one is not a function because it has a free element in the domain that is not mapping. But it is a one-to-one relation still, It's a one-to-one relation, right? A one-to-one relation. Right? So we can say it is a one-to-one relation. Let me write it out. It is a one-to-one relation. It is just a relation. It is a one-to-one relation. You don't quite reach the status of a function yet. For it to reach the status of a function, it has to satisfy that rule. Each element in the domain must map one time alone. That fancy statement that is the people write. Simply means all the elements in the domain must map. And when they map, them can only map one time alone for it to be a function. Good? All right, let's look at the second one now. So answer me again. And when you talk and you don't get it right, you know, that's fine. So don't feel no way. Because we're learning. Right? We learn from our mistakes. There is a reason in your head why you said it was a function. Now you know that that is not the only reason that determines a function or not. It becomes clearer to you now by me explaining it. So don't be afraid to give your answers. Nothing is wrong if you give an answer and it is not correct. Right? You're reasoning it out, improving. It's progress before perfection. So you have to be brave and still say what you mean. Because sometimes when you say what you mean, you give me a chance to explain it better. Right? Because suppose everybody come on and say it's not a function. Then I wouldn't need to spend so much time explaining. Right? It allows me to give more explanation, make it a little bit more clear. All right. So let's go on the second one now. Second one. This one now. Function or not? Tell me. Don't be afraid.
Function.
Function.
Yes, sir.
Function.
Everybody agree that's one a function.
Yes, sir.
And what kind of function?
One to one.
One to one.
Very good.
One.
So the fact that this door in the mapping is irrelevant, don't it? Irrelevant.
Yes, sir.
What would happen at the higher level is that they would say that this is not surjective, but that is not for you. When there's a free element in the codomain, they say it is not surjective. We're not going to see that in a CSEC. So at CSEC, that is irrelevant. Yes. Each element map, and when they map, them all map one time. So no one understand it better now. Right? So this one is a function. This one is a function. It is a function. Yes. It is a function. And it is one-to-one as well. It is one-to-one. It is a one-to-one function. Good? Nice and easy. Talk to me about the third one now.
Not a function.
Not a function.
Not a function. That guy has spoiled it up, don't? That guy, they spoil it. Not a function. So this guy calls it not to be a function because it does not map. Does not map, or it has no mapping. Therefore, not a function. The whole relation is not a function. Not a function. This relation is not a function. Good. What kind of relation is it though?
Many to one. No, never mind.
One to one.
One to
One to one, man. One mapping to one. Good. One to one. One to one relation. It's a one-to-one relation. All right, good. Yeah, man, we're getting better. Let's look at this one now.
Not
Function
a
or
function.
not?
Not a function, sir.
Not a. Which one spoiled it? Which
The
one spoiled
second
it?
one, sir.
Second one.
Very good. This guy right here so spoil up everything. If you map too much time, greedy. So that guy map too much time. So therefore we don't have a function. So this one mapping twice. Right? This one is mapping twice. You can only map once. Each element must map only one time. That is mapping twice. Right? So therefore not a function. Not a function. That guy spoil up the whole thing. Not a function. What kind of relation is it? What kind of relation is it?
One
One
to
to
many.
many.
One to many. Right.
One to many.
One to many. One to many. Relation. Very good, guys. Very good. Get in there. Talk to me about this one now. Function or not?
Yes.
Yes, sir.
Function.
Good. So even though the codomain right here, so have 3 elements in it for free, that is irrelevant. That don't matter. Right? This is still a function. It is the domain that tells you that's a function. Each element in the domain, 3 of them, each of them only have 1 arrow coming off it. So this one is a function. This one is a function.
Many to one.
Many to 1. Very good. This one is a function, and it's many mapping to 1. It's a many to 1 function. Nice. Talk to me about this one now. This last
Not
one.
a function.
Not a function.
Cause it not to be a function.
The domain,
The third
the one.
The third,
one.
the third domain.
Which ones? Which ones? Which ones? Which
Second
element
dot.
is the domain?
The
The
second
third
dot.
one.
Third one. Some
The
people say
second
the
and the
third one
third.
and
The
some
second and the third.
second and the third. Both of them spoil it. They can't just pick out one alone. Both of them spoil it. This one spoil it by not having any mapping, and this one spoil it by having too many mappings. Two of them spoil it. Because in CSEC, they can ask you which element spoil it, you know. Why, which element cause it not to be a mapping, and you have to identify the two of them. That second one spoil it by not having any mapping at all, and the third one spoil it by mapping twice. You see that? So let me mark it. So this one has no mapping. That spoil it. It does not map. And this one has too many mappings. This one mapping twice. So this spoil up bad, bad, bad. This one mapping twice.
One to many.
Right? So therefore, not a function. Not a function. And yes, it is a one-to-many relation. One-to-many relation. Very good, guys. Very good. I know you understand it better by this example. That's why I was drawing this before the class. All right. We're going to look at another thing now. All right. Let me save this. And let's look at another thing now. All right. So we're going to look at the graphs now. You're going to tell me now which is the graph of a function or not. Now remember, look down here. I said vertical line test first. Who can tell me why I would need to do the vertical line test first? Because we have to decide if it's a
to see if it's a function.
Good. Now let me give you an example of how you can get messed up if you don't do the vertical line test first. Right? Let's look at the first one. Let's look at the very first one. Now suppose on the very first one, right? We say, okay, let's do the horizontal line test first. How come? So bam, I'll draw a horizontal line there, so 1 point. Draw a horizontal line there, so 1 point. Draw a horizontal line there, so 1. Any horizontal line I draw, it is intersecting at 1 point, don't it? So I might think it's a one-to-one function because I do the horizontal line test first. You understand me? If I draw a horizontal line test first, I'm going to see only 1 point. Each of those horizontal lines intersecting at only 1 point only. So I might say that it's a one-to-one function. But no, it is not a function. Because if I do it the right way, by doing the vertical line test first, and let's use a different color for the vertical line. Right? Let's do a different color for the vertical line. Let's use the green for the vertical line, which you're supposed to do first. If I draw the vertical line test first, put a 1 on that. For the vertical line test first. I see 3 points intersecting there. And that tells me the vertical line test that I did first, V-line test, because it's intersecting at 3 different points, it is not a function. It is not a function. You don't have a function. Because you have one x value. Let me show you what's in a function. Use a red ink. You have one x value, giving you a y value there, a y value there, and a y value there. See that? One x value giving you 3 y values. One x value giving you 3 different y values. That's what happens, essentially. All right? So it is not a function. And therefore, because it's not a function, you don't even bother to do the horizontal line test. So let's write it. Therefore, no horizontal line test should be done. You don't do it because it's not a function. Remember, the horizontal line test tells you what kind of function you have now. So if something is not a function, what are you going to do the horizontal line test for? You don't need to do an horizontal line test because you have established that it is not a function. So don't bother doing a horizontal line test because you see that the horizontal line test is going to tell you the wrong thing now. Okay, going to make you think that you have a one-to-one function. It's not a function. Don't do no horizontal line test. The horizontal line test is now redundant. Don't do it. Right? All right, so let's look at the next one now. This function, which is a set of points. It's a set of points. Talk to me now. Which test you must do first?
Vertical line test.
Good, and you can see that any vertical line I draw can intersect this graph at only 1 point only. See that? Any vertical line I draw, and this graph is just a set of points, no line or section to it. Any vertical line I draw will intersect the graph at only 1 point only. So I'm just going to leave one of them just to indicate that. So let's just leave this one alone to indicate that. That's my vertical line test. One, do that first. So one, V-line test first. That tells me that we have a function, right? A function. It is a function. Pass the vertical line test as a function. Then we're going to do the horizontal line test second. Let's do it in red. Secondly, we're going to do the horizontal line test. Now look, any horizontal line I draw can intersect this graph only once. See that? Any horizontal line I draw will intersect that graph only once. So if a horizontal line intersects the graph only once, what does that mean?
1 to 1.
1 to 1. So see it here, 2. Secondly, I do my horizontal line test secondly. So the horizontal line test is telling me that it is a 1 to 1 function. Nice and easy. All right, let's go to the next one. Which test you must do first? Which test you must do first on this graph?
Vertical line.
Good. We see it again. Good. See it again. If we run and do the horizontal line test first, it's going to tell us the wrong thing because those vertical lines intersecting only once. Right? So, we have to go now and make sure we do the vertical line test first, guys. See there? This vertical line intersecting twice here and there. Do this first. So our vertical line test says not a function because it intersects twice. Not a function. If it's not a function, remember, no horizontal line test. Therefore, no H line test required because it is not a function. All right, talk to me now. This one down here, what it look like? Anybody can just look and tell me what I think it is?
Many to one.
Into one function.
Many to one function. Brilliant. Brilliant. Because any vertical line I draw will intersect only once. So we can go look faster now. Right? We can go look faster now. Right? And my horizontal line will pass through all those points. So it's intersect the graph more than once. So it's many to one. Very good. So I'm going to leave that one there for the horizontal line. I'll put the 2. Leave it there. All right, we know we'll do the vertical line test first. So let's put it here. All right, 1 and 2. So my vertical line test says we have a function. And my horizontal line test says it's a many to one. It intersect more than once, right? Many to one function. Nice and easy like that. All right, talk to me about this one now. There's a vertical section here, and a vertical section here, and a horizontal section there. What do you think? Function or
Not a function.
Not a function.
Not a
Not a
function.
function.
Very good. Because if I draw a vertical line and a vertical line, it's going to intersect it an infinite number of times. Don't you see there? See that? You're going to intersect it there, so, there, so, there, so, there, so, enough times. So not a function. So any graph that has a vertical section is not a function. Any graph that has a vertical section is not a function. Because a vertical line will intersect a vertical section many times, an infinite number of times. So my V-line test, V-line test is saying not a function. Not a function. All right, and then we know there's no need for a horizontal line test. All right, no H line test. Don't do none. Don't do any. None required. Talk to me now. This one. So these points are on a vertical section. Same thing over here, but there's a set of points, not a curve. There's a set of points. I'm giving you some example that actually set an exam, CXC, These are examples that
Not a function.
Not a function. All right, because a vertical line is gonna come through all these points down here. Let's go back for the green for the V-line test. All right, this vertical line will pass through these points. So one V-line test first. The V-line test says it is not a function. Talk to me, this one. Function or not function, or what kind of function? You can look at it and know now.
Function.
What kind? What kind?
Many to one.
A many to one function. Very good. So any vertical line I draw,
function.
very good. Any vertical line I draw on this one, it's going to intersect at only one point. And you don't go and draw a vertical line up here alone. Remember, it's any vertical line. So you draw it without intersect more than once. I can draw it here, for example. I draw it there, I get in 4 points. All right, so let's go back. One, the V line says it is a function. And the H line, let's go back. 2, which is the H line test, says it is many to one. Last one. Talk to me now, that curve. Function or not function?
Function.
What kind?
One-to-one function. One-to-one.
One-to-one. Beautiful. Nice and easy. Any vertical line I draw will intersect only once. And any horizontal line I draw will intersect only once. And so that's a one-to-one function. So my V-line test first. My V-line test tells me it is a function. And my H line says it is a one-to-one function. All right, so that's supposed to help us to understand it a little bit better, or a lot better. Now these are actual exam questions, right? These came off exam questions. So these that we did here came off exam question where they wanted us to say whether they are functions or not, and what kind of functions they are, and also the mapping diagrams that we did a while ago. These also came off exam paper. All right, so I'm giving a question that came off exam papers. All right, so let's get back now. Let's get back to the business at hand, which is the presentation. All right, so inverse function. What's an inverse function? So we're gonna go into some of the components of the function now, all right, and also some of the application. What's an inverse function? So an inverse function is basically just a function that reverses what a function did. So for example, if you think of a motor car, in a motor car, you have the drive function that allows the car to go forward, and you have the reverse function that allows the car to go backward. So if somebody starts at a point A on a road and use the drive function in the car to move from A to B, right? And that's a function. The drive function moves the car from A to B. And then if you want to go back from B to A, you have to use the inverse of that drive function, which will now be the reverse function. And the reverse function takes you back from B to A. In that sense, the reverse would be the inverse of the drive. And also, the drive is the inverse of the reverse. So the drive and the reverse would be inverses of each other. So an inverse function is just basically, in simple terms, is a function that takes you from the range back to the domain. The function that reverses the mapping. So if a function takes me from a value of 1 to a value of 10, then the inverse function is a function that will take me from a value of 10 back to a value of 1. And it can take the form of a formula just the same. And we have to actually be able to calculate it as a formula. But so another way of saying it is that it's like the x and y values switch around from the function, between the relationship between the function and the inverse is that the x and the y values switch around, the trade places, they switch around. All right, but make a look at it. Make a look at it. So the inverse of a function firstly is written like this. So the inverse of f of a function f is written like that. The inverse of g is written as g to the minus 1. The inverse of h is written as h to the minus 1. The inverse of k is written as k to the minus 1. So the minus 1, put the minus 1 on here in function means the inverse. It means that we're talking about the inverse. All right? So that's the first thing, how we represent an inverse function. We put the minus 1 up there, a small minus 1, superscript minus 1. And they say no, and is the function. So the inverse function is also a function, you know. That's the thing, you know. The inverse function is a function. So in the car, the drive is a drive function that carries you forward. The R, the reverse, is a function that carries you backwards. But both of them are functions. It's just that they do the opposite to each other. The reverse what each other does. But they are both functions just the same. So the inverse function, f to the minus 1, is a function that will map the range of f back to the domain of f. Right? So the inverse of f will map the range of f back to the domain of f. All right? So this is obtained mathematically by interchanging the x and y elements in the ordered pairs. So the function that reverses the x and y in the ordered pairs is the inverse function. All right? So if I have a function, if the function is f is 3x plus 1, f of x equals 3x plus 1, or f is such that x maps to 3x plus 1, then these will be the ordered pairs. for that. If these could be a set of ordered pairs. We're not choosing all of them, just these 4 ordered pairs, 4 ordered pairs, right? And everybody understand how we'll get those values. Let's do a couple examples to make sure everybody on the same page. So this one, for this one to go to this, it is 3 times minus 1 plus 1. Everybody see that? Okay, we're using this relation. 3 times minus 1 plus 1. For this one to go to this, it is 3 times 0 plus 1. For this one to go to this, it is 3 times 1 plus 1. So that is 4. And for this one map to this, it is 3 times 2 plus 1. 3 times 2 is 6, 6 and 1 is 7. That's how the map is. That's how we have those pairs. All right? The x is mapped onto 3 times the x value plus 1. So that's how we have those pairs. The inverse function now would have these pairs. Bam! The inverse function f to minus 1 would have those pairs. So you see that the pairs switch around. This range become the domain, and this domain become this range. This range become this domain, and this domain become that range. This range become that domain, and you see them switch. This becomes this, that becomes that. The pairs switch value. All right? The pairs switch value. So let's bear with me with this thing, please, sometimes. So the question is, this is a formula. This is a formula that map these values onto these values. You see the formula now that's going to map the -2 back to -1, and map the 1 back to 0, and map the 4 back to 1, and map the 7 back to 2, can be calculated from this formula mathematically. Can be calculated by simply interchanging the x value and the y value in the formula and then transposing to make the new y formula the subject. So finding the formula that does these is finding the inverse function, finding the formula for the inverse function. And that's what you'll be required to do in the exam, right? Most of the time, to calculate that inverse formula, that inverse function formula, all right? So since the inverse, remember I told you that both of them are functions. Since the inverse is a function itself, only a one-to-one function can have an inverse. Since the inverse must be a function itself, only a one-to-one function can have an inverse. I'm going to explain that a little bit more just now so you can understand it. See there? A one-to-one function can have an inverse, but a many-to-one function cannot have an inverse. And let me show you why now. Pay attention now. Let me show you why over here on the right side. I'm going to show you why over here. Let me use this and show you why. All right, look here now. Pay attention now. So let's say you have let's say a function is 1 to 1. All right? So it's basically this one mapping to this one. When you form the inverse function f to the minus 1, it is reversed. 1, 1 to 1. The mapping is reversed, so you get back 1 mapping to 1, which is fine. But if the original function, watch it now, you know, the original function was many to 1, and you try to form the inverse, let's say you try to form the inverse, and you still put back the many to 1 down here, as we did at the top. This one down here, many to 1, is good. That is a function. But if we try to reverse the mapping and go 1 to many, what did we say? 1 to many is not a function. Don't it? Not a function. Right? Not a function. And because we said the inverse has to be a function as well, this would not be a function down here. And that is why we say a many to one function cannot have an inverse, because if you reverse the mapping, you're getting one-to-many. And one-to-many relation is not a function. This up here is good, and this is good. Down here, so it's spoiled over here because the relation becomes a one-to-many. Well, the neighbor's child making a lot of noise. Right? So that is why only a one-to-one function can have a function. But understand that little reasoning right there? But understand that little reasoning as to why only a one-to-one function can have an inverse? The point is that the inverse function also has to satisfy the definition of a function. I remember, you know, one-to-many cannot be a function, you know. So if you have a many-to-one, and you reverse the mapping and it becomes one-to-many, the one-to-many is no longer a function. And what we're saying is that the inverse also must be a function. So in that sense, the inverse would not be a function because it would now then be a one-to-many, which is not a function. So therefore, only a one-to-one function can have an inverse. All right? Because if you flip the one-to-one, it's still getting back a one-to-one. All right? All right. So how do we do it now mathematically? That is the question now. How do we do it now with the equations mathematically? All right. So f to the minus 1, right? To find f to the minus 1 in terms of x, we interchange the x with the f as follows. Now, some teachers use x and y. I tend to keep back the f, and I can tell you why. Because sometimes in CSEC, you will be working sometimes with two functions. One function, they give it to you with a f, and the other one, they give it to you with a g. So you have a f of x and you have a g of x. Most times in CSEC, those are what you get, f of x and g of x. And you might have a point where you have to find the inverse of both of them, the f1 and the g1. If you call the two of them y, you might end up mix them up. If you call the two of them y, no, a lot of teachers teach the inverse function that way. They call the fy, right? And then they interchange the x and the y, and then they solve to make y the subject. I know that's how they teach it in the school for persons who learn this already. But my issue is that what I've found in the past is that students, when they call the fy and also call the g function y, they end up mixing up the two of them. Now, when I call the inverse of f to the minus 1, I know that that is the inverse of f. There's no mix up there. And when I call the inverse of g to the minus 1, I know that that is the inverse of g. There is no mix up there. So I don't tend to introduce the y into when I'm doing inverse function. I just write f to the minus 1 for my inverse of f and g to the minus 1 for my inverse of g, and keep it simple. Now look here now. So if your function is this, what I do, to do the operation, I leave off the of x expression here. Because I know that I'm working with a function of f. I leave it off and I write this when I'm going to do my inverse function operation, because this can complicate it. I don't want to mix this of x with the domain x that this is. All right, this is just like a statement that says a function of x. You know that you're working with a function of x. That's all that is. So I tend to leave that off and just work right back this as this right here. All right, right here. And I'm working with that. And then now, remember, the inverse function is formed by interchanging the domain and the range. Now remember now, the x right here represents the domain, and the f right here represents the range. All right, represents the range. And when you switch them around, what is supposed to happen is that this is supposed to become the range in the inverse function, f to the minus 1. Now this is the range of f, you know. And this is what the x is now, the domain becomes the range, and this now is supposed to become the domain. And the domain is always written in terms of x. All right, but the range is written in terms, the range of the inverse is written as f to the minus 1. All right, so let me show you what happens now with it. So all that happens when I form my inverse function, that I write that simple. So where the f was, which is my range, I now put x, which is my domain. And where the x was, which is my domain, I now put f to the minus 1 because it is a range in my inverse function. This is my original function right here. This is now my inverse function. just that I don't yet have f to the minus 1 as the subject. And so I have to transpose this now and make f to the minus 1 the subject. All right? Simple as that. All right? So, when you make f to the minus 1 the subject, like that. That's it. Now, if you look, let me show you. So, this is the inverse one right here now. So, how I do it, I have f equals 3x plus 1. I form my inverse function. The f, which is the range on the function up there, becomes the domain in the inverse x, equals the x, which is the domain over here, becomes the range in the inverse function. I put by the 3 and put f to the minus 1. I know of the range, and I put back plus 1. That is it. And then I'm just trying to make this a subject. How do I make this a subject? Carry over this one over this side and subtract it, and then divide under the 3. Let's look at it. Easy, easy, easy. Carry over the 1 first, I get x minus 1, and then divide under the 3, I am left with f to the minus 1. That's what I have over here. That's what I have over here, right here. All right? And then because I have f to the minus 1 equals this now, I just write f to the minus 1 equals x minus 1 over 3. And then I can just put in back of x. Put back the of x that I had before right here. Because the inverse is also a function of x. All right, as simple as that. And that's my inverse function. All right, but let's look at the mathematics a little bit more. So that is how you actually calculate the inverse function. But let's look at the mathematics so we can see the numbers how they work. So I've just worked out that this is my function and this is my inverse function, right? Right? So this is the inverse of this and vice versa. They are inverses of each other. All right? All right, I don't know why that is on the screen now. Let me go. Let me see. All right, it's gone. All right. Erase all again. All right, so those are my inverse functions. Now I'm going to put up the values now, the mapping diagram for both, so we can understand a little bit better. So this is the mapping diagram for the functions, right? For the function on the left. That's the mapping diagram for the function. So the -2 map onto -5, the -1 map onto -2, the 0 map onto 1, the 1 map onto 4, the 2 map onto 7. And I showed how we calculated those values. Now, how the inverse function work is that what we have done, we have got this formula for the inverse function that is now going to reverse the mapping. Right? And I'm going to show you for each one the inverse function I'm looking at now. So look at the right side, or show you that inverse function actually works. Right? In the inverse function, which is f to the minus 1, let me use the purple ink. The inverse function, which is now f to the minus 1, I'll make it darker still. F to the minus 1 equals x minus 1 over 3. We calculate that as our inverse function. This now, this function, this inverse function, is going to map the values that were the range back to the values that were the domain. So let's look at it. Firstly, remember it is 1 point. 1 point was I want to present a way that makes sense. All right. So 1 point on the function. 1 point on the function was -2, -5. Let's just call it. Let's put f in it first to know it's a function. So all one knows that the formula, what formula will map this back to this? That's what we're looking at. And this is the formula up here. So how it works. The inverse function, if you apply the inverse function with a -5, it's going to put -5 up here, -1 divided by 3. And so that becomes -6 over 3, which is -2. So you see the inverse function is mapping the -5 back to the -2. That's what we see. The function did this, you know. And the inverse, this inverse up here is now doing this. Right? Let's do another value. Let's look at let's look at the 2 and the 7. Let's look at the 2 and the 7. So the function mapped the 2 to the 7. Let's write how it did it. Because remember, the function was f equals 3x plus 1. So the f of 2 was 3 times 2 plus 1. That's how f of 2 is equal to 7. So see, f of 2 is equal to 7. So the inverse function now, f to the minus 1, is supposed to reverse it. It's supposed to map the 7 back to the 2. Let's show how that works. The f to the minus 1 formula is x minus 1 over 2. Let's put a line between here. X minus 1 over 3, sorry. So the f to the minus 1 of the 7, we're trying to map the 7, show that the 7 is mapped back to 2, becomes 7 minus 1 over 3. 7 minus 1 is 6 over 3. 6 over 3 is 2. Right? So you see that the inverse maps the 7 back to the 2. So the inverse is a formula that maps the original range values back to the domain values. And I want you to note something now. Look at this now. The range of f is now the domain of f to the minus 1. Same set of values. And the domain of f is the range of f to the minus 1. All right. So the input value over here, the output value over here becomes the input value over there. And the input value over here becomes the output value over here. The input over here, the in over here becomes the out over here. And the out over here becomes the in over there. And this formula is a function, and this formula is the inverse. And this formula over here will take the out values and carry them back to the in values, the output values, and take them back to the input values. That's what happens with the function and the inverse. All right, so let me clear the screen. I'm going to actually calculate some of them, you know, so bear with me. So see there, the domain of f to the minus 1 is equal to the range of f. That's what I just said. The domain equals the range, right? And those are the values right here. The -5, the -2, the 1, the 4, and the 7. And the range of f to the minus 1, that is this one now, let me just underline it, is what the domain was over here. And those values are the -2, the -1, the 0, the 1, and the 2. And that's how the formula works. All right? Hope you understand. So the map, they reverse the mapping. They are the functions that reverse the mapping. They are inverse functions of each other. Let's talk about the relationship. All right? The relationship. And it's something that they ask in CSEC all the time. What is the relationship between a function and its inverse? And you have to remember, it's something simple. All right, I'm going to tell you now. First time I'm introducing this now, the relationship between a function and its inverse. The answer is that they are reflections in the line y equals x. The relationship between a function and its inverse is that one is a reflection of the other in the line y equals x. This is the answer. The relationship between a function and its inverse. All right, the relationship between a function and its inverse is one is a reflection of the other in the line y equals x. Now, I know we don't learn about how reflecting line y equals x yet. But when you're reflecting the line y equals x, x and y values switch around, and that is why the relationship is between them is that when you reflect the line y equals x on a graph, the x and y values will switch around. A point, for example, that was 1, 3, will switch around to 3, 1 if you're reflecting the line y equals x. And that is why that is a relationship between a function and its inverse. They are reflections of each other in the line y equals x. I mean, we're going to repeat this multiple times again, but I wanted to get it from now. So let's look at this example. So let's say a function has the points 1, 7, 2, 4, 3, 3, and 4, 2.5. Then the inverse function, we're going to have those values. 7, 1, 4, 2, still 3, 3, because if you switch around 3, 3, it's going to be 3, 3 still. I hope everybody see that. And then 2.5, 4. Then now, if I show it on a graph, so let's look at the graph right here. I'm going to put the points on the graph. So let me close this up. Let's make this and close this and minimize this. All right, let's look at the graph. All right, so if I'm going to show those points on the graph now, so everybody pay attention. So those are the points for F. So 1, 7 is right here. Then 2, 4 is right here. Then 3, 3 is right here. Then 4, 2.5 is right there. See there, 4 is x value 2.5. This is 2 and this is 3. So 2.5 is right here between them. All right. So basically, those are the points. I'm trying to, I can never control this thing. I don't know what to do. I'm trying to clear the screen. All right, see there. Erase. All right, so I'm plotting those points. And that's the graph of the function, f. If I plot the points and draw the graph, those are the points. If I plot the inverse f to the -1, I'm going to do it in red. Those will be the points for the inverse. You can look at it clearly and you can see. So for example, the point down at 7 is 7, 1. If I draw the curve through those points, that is the inverse. If I show the line y equals x, and line y equals x is a line that passes through points where the x and the y values are the same. That is the line y equals x. See, it passes through the point 1, 1 right here. Pass through the point 2, 2 right here. Pass through the point 3, 3. That's what's on the function. Pass through the point 4, 4. Pass through the point 0, 0. Pass through the point 7, 7 right here. Where is it? 6, 6. 6, 6. 5, 5. 7, 7. 8, 8. That's the line y equals x works. Pass through points where the x and the y values are the same. So like 3, 3. Pass through points where the x and the y value is the same because the line y equals x. On that line, the y value and x value is the same. Now, if you look at these two graphs, you can see that is like the line y equals x is like a mirror line. It's like a line of symmetry. Right? The two graphs are reflections of each other. So this point, for example, reflects over the line to this point. Right? This point up here reflects over the line to this point. They reflect the same distance. It's like a mirror line. Same distance. The points are reflections of each other in that line. Right? So that's the relationship between them. They are reflections of each other in the line y equals x. And it's something that is very important for you to remember and know. The relationship between a function and its inverse is a reflection of each other in the line y equals x. And it's going to be in the classwork on Wednesday. Well, yeah, it's going to be in the classwork. Right? Relationship between a function and its inverse. So it's something that you have to know. All right. So the intersection. Now this is not really, you don't really need this, but it's good information to know, but you don't need it. The intersection, which is the point right here. Intersection. The function and its inverse intersect the line y equals x at the same place, and that is the point 3, 3. Remember, if you switch around the point 3, 3 and the function is the same point 3, 3 and the inverse, because it's 3, 3, if you switch around 3, 3, still 3, 3. All right. To find that point, you can actually solve the equation f of x equals x. Right? So if I put this, whatever the function was, just solve the equation f of x equals, but don't worry too much about this part down here yet. When we get the opportunity, we'll come back to that. I don't want to focus too much on that, but that's where you can find that point. Solve the equation f of x equals x, and you get that point because it intersects the line y equals x. All right. So we're going to do these two examples now, guys. These two examples. We're going to find the inverse of this. I'm going to find the inverse of this nice one right here. This one requires more steps. All right. That one requires more steps. So it's very nice and easy. Let's look at it. All right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let me make this small again. All right. And all right. So let Share the screen. And then we're going to do it over here. All right. Can't do this thing sometimes, you know. Let's take another one and see. About the same size. All right. All right. So maybe what I need to do is copy it and copy this onto the full screen. I'm doing these two. So. Just bear me a second, guys. Just bear with me. Bear with me. All right. Let me copy them again. All right, so I want to do these two examples. I'm going to find the inverse of those two. All right, using the very same procedure. Using the very same procedure for both of them. These two functions right here, G and F. All right, I'm just interested in finding the inverse, forming the inverse function. This one, as I say, requires more steps. All right, and it's something that you need to practice. When I set this one, is usually in section 2. This one, section 1. All right. All right, so let's go. And it's just your ability to transpose. I'm going to do it the easy way. So pay attention. So they give us g of x equals 3x plus 2. And I want us to find the inverse function. As I said, I'm going to write it as just g first. G equals 3x plus 2. Just leave off the of x there for the time being. We know that we're working with functions of f. And then simply, I'm going to form the inverse function. I usually do that to indicate that I'm forming the inverse function. So I'm interchanging the domain and the range. This represents the range and the inverse function. It becomes the range and the function become the domain and the inverse function. And this represents the domain on the function. It's going to become the range and the inverse function. So I'm going to put 3, and for the x, I'm going to put g to the minus 1. Some teachers put y. I don't like putting y, and I explained to you that already. So I'm putting g to the minus 1 plus 2. And then this is a function, you know. This is the original function, you know. And this is my inverse function. But all I need to do with the inverse function now is make this a subject. Transpose and make that the subject. This is how the g is a function up here. I need to make g to the minus 1 a function down there. So I need to transpose that. All right. So to transpose that now, simple. It's simply linear. I'm going to carry over the 2 and subtract it, and then I'm going to divide under the 3. Hope everybody can see. If I don't see it, let me know. So I'm going to get x, carry over the 2 becomes minus 2, and then divide under the 3. That leaves me with g to the minus 1. Everybody see that? If you don't see it, let me know. Everybody understand that? Good. Yes. All right, good. So now that I have it, I can say that is, i.e., that is g to the minus 1 is x minus 2 over 3. And now that I'm done, I'm going to find it. I can just put in back the of x that I left off up here. The of x. Put in back the of x. I'm working with functions of x. And that's my inverse function right there. I have it here, you know. But just that I don't yet have g to the minus 1 as a subject. So I've converted to this one now, which has g to the minus 1 as a subject, which is what CSEC is going to want. Simple as that. Right? It's the same function, same inverse function, but I just need to make g to the minus 1 subject. So we'll do that. That's the inverse function. Let's do the F1 now. And F1, as I said, will require more steps. So pay attention. All right? F1 will require more steps because it's called a rational function. All right? And there's some other things. This is called a rational function because it comes in the form of a fraction, a ratio. It's a function on another function. And so it's rational. This one is linear. All right, that one is a rational function. And I like to give rational functions all the time. All right, so we're going to go now. So they give us f of x equals 4x plus 5 divided by x plus 2. And I want to find the inverse of that function. Same procedure. I'm first going to write it as f equals 4x plus 5 divided by x plus 2. I'm going to write it as that first. All right? And then I'm going to form my inverse function. Pay attention now. So it's basically forming my inverse function. So this is my function up here. And I'm forming my inverse down here. When I form the inverse, this is the range. It becomes a domain. So it becomes x. This x and this x, each of them represent domain. Each of them now is going to be interchanged into range in the inverse function. So I become 4f to the minus 1 plus 5 over f to the minus 1 plus 2. This is my inverse function. All right, so don't let the f to the minus 1 and f to the minus 1 create any problems for you. Just some teachers write y, right? But I don't want to mix them up, so I just leave it as f to the minus 1. And then all I'm doing now, I'm transposing to make this and this the subject. I want that to become the subject. I only want one of it in the expression. So to do that, I have to expand out the expression, expand out the equation, sorry, and transpose all the terms with f to the minus 1 on one side and everything else on the other side of the equation. That's what I have to do. I have to expand it out first. What's my first step in the expansion? What's my first step in the expansion? My first step in the expansion is to multiply this entire denominator across here by the x. I'm going to go step by step. All right? I'm going to go step by step. So I multiply this thing across here by the x first. So I'm going to get x times f to the minus 1 plus 2 equals 4 times f to the minus 1 plus 5. But understand that? First thing is to multiply the denominator. So let me write it. Multiply by the f to the minus 1 plus 2. That's what I did to go from here to there. To go from here to there. That's what I did. All right. Then after that, I'm going to expand out this bracket because I tried to get the f to the minus 1 terms isolated. All right. So I'm going to expand the bracket. I'm going step by step. So I get x times f to the minus 1, and then the x times 2 is plus 2x equals 4 times f to the minus 1 plus 5. Now we'll get better at it. We can leave out this step. All right, we'll get better at it. This step we don't have to show it, but let's go. When first time we're doing it. Now what we want to do now, we want to transpose this with the f to the minus 1 over onto this side and subtract it. Subtract it. We don't want the 2x over here. We're going to take it over onto this side and subtract. Remember, when you transpose, you subtract the signs. You change the signs, right? Not subtract, you change the signs. So already know. So I have x times f to the minus 1. I'm going to get minus 4f to the minus 1. That's because this comes over here and subtract, right? And then now I'm going to get equals, the 5 is there. So I'm going to put by the 5. And then this now goes over here and become minus 2x. So I get minus 2x. So let me show the red again what happened. That is because this now comes over this side and becomes minus. That's what happens right there. Nice and easy, nothing complicated. All right, go back for the purple. What happens next? I'm going to factorize out the f to the minus 1 out of these two terms. I'm trying to make f to the minus 1 a subject. So I'm going to put f to the minus 1 bracket x minus 4 equals the 5 minus 2x. All right? But I say that. I factorize out f to the minus 1. Then all I need to do now is take this and divide it under this side as a whole. It's basically like the same as if you are dividing both sides by x to the minus 4, you know. The same thing, you know, and then them cancel here, so I left with that. All right, shortcut method is to say that because this is multiplying right here, you divide it under that side, right? So in any case, what would happen next is that your f to the minus 1 will be left on this side equal to 5 minus 2x over the x minus 4. And now that I'm finished, I can put in back the of x. And that's it. All right, let me turn the camera vertical so you can see it, all of it. See there? That's it. That's what we did. So look back at it. Right? Starting right here. Right? First we do the inverse, interchange the domain and the range. So the f becomes x. The x here and here each becomes f to the minus 1 and f to the minus 1. So all we do so far is form the inverse function. But after we form the inverse function, we need to make f to the minus 1 the subject. We need to make this a subject. So we're going to have to transpose it. All right? When you transpose, you have to expand it out first. And then after expand it out, you group the things that you want on one side and everything else on the next side. So multiply this first, this whole denominator over onto here by the x. That's how we end up with that. And after we do that, we expand it out, expand out this to get that. Then after we expand it out, we're transposing. So we take this 4f to the minus 1 over onto this side and it becomes minus. And we take this plus 2x over onto this side and it becomes minus 2x. And we see that. And then what we do now, we'll factorize the f to the minus 1 out of these two terms. Factorize out the f to the minus 1. And that's how we get the x minus 4 in the bracket. And then to leave f to the minus 1 as a subject, we take this and we divide it under here, x to the minus 4. And that leaves f to the minus 1 as a subject. That leaves this f to the minus 1 as a subject. And I will just put in by the of x last, because the question will say find f to the minus 1. If I leave it without that, it is still correct. No problem. It's the same thing. But I put it there or I leave it. And basically, that's it. But good. You just need to practice it. So these questions, you go back home and you work them out by yourself, please. All right, that's what you do. Work them out by yourself. The one at the top was pretty straightforward, that one. Simple. Let me take off these red things so you can see it again. All right, for this one up here, let me use the red ink again. All right, so for this one up here, same thing again. This is my function. I just leave off the of x first to do the work. All right, then I form the inverse function. What happens when I form the inverse function? The range becomes the domain in the inverse function, becomes x down there. And this is the domain of the function, it becomes the range in the inverse function. Just that range in the inverse function, we put the minus 1 on it. So I have formed my inverse function here, that's my inverse function, but I need to make this a subject. So I have to transpose and make it a subject. Easy transposition when it is linear like this. Carry the negative, carry the 2 over here, and it becomes negative 2. And then I divide under that. Okay, let me show you the steps over on the right side. Let me show you the steps. What would happen if I in these steps right here is that when I have x equals 3g to the minus 1 plus 2, I'll carry over the 2 first. I will get x minus 2 equals 3 times g to the minus 1. Then I need to divide both sides by 3 to cancel this one. That's what happens. Right? But instead of saying that, I just said divide it under here. Divide it under there. That's a shortcut we have seen the same thing. Divide both sides by 3. So I get g to the minus 1 equals x minus 2 over 3. So let's basically leave out that step. And at this level, you can leave out that step. All right. There's some steps that you're not going to get any extra marks, so you can leave out. All right. That's that. All right. What time is it now? That time, all right? It's almost 3 as we're going now. I plan to do some more today, you know. What you guys think? Let me see what is supposed to come next. It's almost 3 o'clock. I'm not rushing because we have an additional day. I mean, we can always do some more tomorrow. So I don't want to rush. All right. So I think what is supposed to come was the composite function. Let me look and see. Let me see. So I did that. All right, the composite function, which is function of a function. All right, I'm going to skip through and show you. So what's supposed to do? Composite function. Composite function, right? I was supposed to do composite function here. And composite function and image of a composite function. It's just 3 more slides left to finish the class, you know, and then reach homework, you know. What do you think? Let's go through it and finish. What do you guys think?
Yes, sir.
Let's go through it and let's finish it. All right, we can always reinforce tomorrow, right? If necessary. So we're going to do the composite function, which is just basically a function of a function. All right, and that way you'll be able to do the homework. We can focus on the examples tomorrow. All right, and reinforce this just the same. All right, so we could continue. Not a lot left, just composite function. So let me erase this. All right, so composite function is a function of a function, like 2 functions, one follow the next. All right, and it's like I like to give students the example of a washing machine, but you know I don't need to get into that no. But you know, like you have 2 washing machines, one that washes the clothes and one that dries the clothes, and it's 2 separate machines, right? But then you can have a combo machine where it has the washing part or the washing function and the drying function in one. And that combo machine must know that it has to do the washing first before it does the drying. Otherwise, the result that you get out of the machine not going to be what you want it to be. Just think of it. The combo machine must know that it does the washing first and then it does the drying afterwards. If it does it the reverse way and go and do the drying first and then do the washing, you're going to end up with wet, clean clothes when what you really want is dry, clean clothes, right? So that's a composite function, 2 functions in one. So it's a matter of which one comes first, right? What comes first and how do you represent it mathematically, right? So let's look at it. So a composite function, f of g. So in a composite function written like that, f of g, it means g followed by f. So the one that is on the inside here is the one that is done first, right? Means g followed by f. So f of g means g first, f afterwards. G first, f afterwards. They apply the g function first, and they apply the f function afterwards. That's what f of g stands for, f of g. If I write g of f of x, then this would mean f followed by g, the one that is closer to the x, you do first. It's like the x is a clothes, and the f is the washing machine, and the g is a dryer. Up here, so the g is the x is the clothes that they're operating on. The g is the washing machine, and the f is the dryer part. All right. So you want to do the g first before you do the f. All right. And you can make 2 separate machines, and you can make a combo machine, and the end result must be the same. Whether you do them separately or you do them as a combo. All right. So that means apply G first, and then apply F to the result. So after the washing machine wash the clothes, you're gonna have clean, wet clothes. So you put in the clothes dirty and dry. That is the X in there. You put it in dirty and dry. And then the G, which is the washing machine, operate on the clothes. Do what it's doing to the clothes. You wash it and clean it. The result is wet, clean clothes. And then you take the wet, clean clothes and you put it in the F now, which is the dryer. And the dryer does what it is doing now to the wet, clean clothes and give you clean, dry clothes. The F. All right, so that's what happens. So you take the result, what after the G you finish with the clothes, you put it in the F. All right, and you get clean, dry clothes. In this case, G is called the inner function or the first function. When it's F of G, G is called the inner function or it's called the first function. So it's like the washing machine. The G is like the washing part, right, of the machine. And then now the F is called the outer function or the second function. That is what is going to take place second. The F is going to take place second. So that is like the washing, the drying part now. I'm going to dry the clothes second. All right. So this is it now. So this is my clothes. Put it in the machine. And the washing take place first. And so my result, that is G of X. That's my wet, clean clothes. Then the wet, clean clothes now go into the drying part. The drying function take over now. And the F now is operating on all of this thing to give me this final result, which is now my clean, dry clothes. All right? That's just a simple way of trying for you to understand what is happening. All right? So the G operates on the X to give me G of X. And then the F operates on the entire G of X to give me now this F of G of X. It's like the G operates on the F. All right? That's a composite function. All right? Now, this is doing it in two separate steps, like using two separate machines. And this is one machine to give you the same result. Take the wet, take the dry, dirty clothes, put it in the machine. At the end, I have clean, dry clothes. Right? One machine. So the one machine is a composite machine. This down here is my composite machine that does everything in one move. Just put in the clothes and get all the result that you want. This is like you put it in a washing machine, take it out and put it in a dryer separately. All right? So basically, that's what we're talking about. So it's like you have two moves. You have to move the clothes twice. And that is one move. You move the clothes one time. Just put it in there and get the final result. So the composite machine is my machine that has the washing and the drying function all built into it. There's the washing and the drying all in one. All right? But even within it, it has to know that it has to do the washing first. So how do we do that mathematically now? So you have F and you have G. So they give me a F function mathematically as that and a G function mathematically as that. All right. If I want to find G of F, then that is how we say it. G of F of X. That's how you say this thing. G of F of X. I obtain that mathematically by substituting the G into the F, the inner function into the outer function. That's how you do it mathematically. Substitute the G into the F. It's going to do it on the slide, but I'm going to actually work it out so you can see it. All right, so let me clear the screen and work it out so you can see it. All right, so I'm going to form G of F. I'm going to form F of G with this function, with these two. So let me show you step by step. I'm going to do it simple. Maybe the slide a little bit more complicated than I'm going to do it now. So I'm going to form two functions with that. All right, and they might just finish a little bit quicker and understand. So let me do it right here. All right, so I'm going to form the two functions, F of G, and I'm going to form G of F. So I have those two functions. Let me form G of F of X on this side. All right, So let me show you now. I'm going to write them out and show you. So the f of x is 2x minus 1, and the g of x is 3x plus 2. And I want to find g of f. Now, what did we say this means? This one, say it with me, this one means f into g. This one into this one. Or is the inner one into the outer one? That's how you do it mathematically. So if I'm doing f into g, how do I do it now? It means that I'm taking this. I'm taking this. I'm taking all of that f is. I'm bringing it right here. Because I place it here, I place it here for the x, That's what this is, With x was, I put f of x there. So I also have to place it here as well. All right? But let's not complicate it. So what it means, I'm putting f into g. This is my f. And it's coming right here. Simple as that. That's why I put f into g. Comes right here. Just like how we did the substitution the other day with the simultaneous equations. That's it. Because g of f means f into g. You take the f function and you put it in g right there. And this is what you get. So g of f of x becomes f into g becomes 3 times the f is 2x minus 1 plus 2. But understand that? That is the result of that. When I put f into g. G of f is formed when I put f into g. And then I just work it out. So this becomes 3, 2 is 6x. 3 times minus 1 is minus 3 plus 2. That is 6x minus 1 plus minus 3 plus 2 is minus 1. That is minus 1. Simple as that. And then if I do the other way around on this side and do f of g of x, because if the machine dry the clothes first, the result must be different, All right. So I'm gonna show you that the result is gonna be different. So this one means g into f. That's how it works mathematically. This one means g into f, the g function into the f function. Let me write about the two of them again. Remember that the f of x is 2x minus 1, and the g of x is 3x plus 2. 3x plus 2. And now I'm putting g into f. So I'm taking all of g. I'm bringing it and put it into the f right there where the x is. So you put it where the x is. You put all of g where the x is. And put an arrow on it right there. Put an arrow on this one as well. This is how we did the substitution. G into f, where the x is, we're substituting. All of g goes where the x is. I just need to practice this thing. So my f of g of x, when the g goes into f, it becomes 2 times, where the x is now 3x plus 2 minus 1. Because you have placed g into f, and this is the result after placing g into f. That's what this becomes. And you work it out. G into f. F of g means g into f. So this becomes 6x plus 4 minus 1. 4 minus 1 is 3. So I get 6x plus 3. I know that these two things are not equal, not the same. One is 6x minus 1, one is 6x plus 3. But you cannot get the same result if you if you dry the clothes first. So we say note that the g of f of x is not the same as f of g of x. The result is different. Let's think of the washing machine. If you dry the clothes before you wash it, you're gonna get a different thing coming out of the machine, right? If you reverse the order, you're gonna get something different coming out of the machine. All right, so that is that. So that's basically that is a composite function. But the next thing we have now is image of a composite function. So let me go back to the PowerPoint now. Let me go back to the PowerPoint. All right, so I'm gonna just skip through these because it's giving the same result as we just did. See, I think it's easier what I just wrote. It's even clearer. Switch them around. You get that. And then I say that they're not the same. So what I just wrote out for you is the same thing that is on the slide now. All right. Bam. Image of a composite function. Now, what does this mean? This is now talking about the values. You put in the values, what you get out. Right? So like what we did, when we had, for example, f of x equals 2x plus 4. All right. I want the image of 2. In other words, the image of 2. The image of x equals 2. You put f of 2. The image of x equals to f of 2, which should be 2 times 2 plus 4, which this is 8. So f of 2 is 8. So the image of 2 is f of 2, which is 8. Now we're talking, this is now simple functions. That's an image of a simple function. Now we want the image of a composite function. And there are two ways to work out image of a composite function. And it's pretty simple and straightforward. Because it's the same sort of substitution you have to do. You have two methods. You can do the image, you can do the individual functions first, or you can do the composite function first. All right. So method 1 is to find the image of the inner function first. All right. So let's say we're doing that, and I'm gonna do it again. I'm gonna do this for you on the slide. All right. I'm gonna do it and just write it out for you. So let's follow. I'm trying to find these two functions right there. Let me work it out for you instead of doing it on the slide. All right. A second. All right, sorry about that, guys. All right, so let me do this example for you. The image of the composite function, right? Which is, in other words, what value are we getting out? We'll put a value in a composite function. So let me show you. Nice and easy. All right. So there are two methods. You can form the composite function first, or you can do them individually first. Find the image of the inner function first. Now watch this now. So we have f of x equals 2x plus 5. I will have g of x equals 3x minus 1. And we're trying first to find f of g of 2. Now, what this means is that you have to do, if you're doing it step by step, then you have to do the g of 2 first. Because remember, you know, f of g means g followed by f. Right? So you have to do g first. So in this case, this is the same as f of g of 2. So we have to work out the g of 2 inside here first. So then this becomes f of, and then g of 2 now means that we'll put 2 in the g function. That's the g function, you know. So g of 2 simply means 2 in the g function. So it becomes 3 times 2 minus 1. I'm working out what that value is. So it becomes f of, this is now 3, 2, 6 minus 1 is 5. So we're now working out f of 5, because this became 5. Right? And now that we need f of 5, we're going to go and just write f of 5 now by putting the 5 now in the f function. So we're doing f of 5. 5 in the f function. And so it becomes we'll write the values. F of 5 becomes 2 times 5 plus 5, which is equal to 15. That is method 1. All right. Now let's do the same thing now using method 2. Now for method 2, what I'm saying is that to find f of g of 2, I find f of g of x first. This is method 2, you know. Method 2. Let's call it or. Or for the second method, I'm saying we can find f of g of x first. And after I find f of g of x, then I put 2 in the f of g of x. But what does f of g mean again? F of g, remember, means g into f. All right? So the g into f, let me write them out for you. Let me just write them out for you. The f is 2x plus 5, and the g is 3x minus 1. See there? The g is 3x minus 1. That's what I've written here. I just leave off the affix. I don't need to put it. And the f is this. I'm just showing you how I would form it, right? So if I'm forming, let's go back for the red now. If I'm forming f of g of x, I have to put the g into the f. So let me write it now. I would have to put the g into the f. So I'd have to take this g and put it into the f right here. All right, that's what I would have to do. G into f. When I put g into f, my result is 2 times, where the x is, I put the 3x minus 1 and then put back the plus 5. And I work it out, I would get 6x minus 2 plus 5, and then the 5 minus and the minus 2 there is 3, so we get 6x plus 3. That will be my f of g of x. F of g of x. Then I put in the 2 now, so I said therefore I want f of g of 2, you know, therefore, remember that's what I want in f of g of 2. Therefore, f of g of 2 means that I'm putting 2 right here now. And it will become 6 times 2 plus 3, which is the same 15 that we got over here. All right, that's it. So I can do it using the step by step. I prefer this way. If they don't ask me to find f of g, they don't ask me to find f of g first, they don't ask me for that, I am doing it this way. For me, it's quicker. All right, it's quicker. I'm just working with the numbers. Let's do the g to the minus 1. Let's do this one now. The g of f to the minus 1. Let's do it. Let's do that one now. G of f to the minus 1. So let's go up again. All right, so let's write them again. So I'm going now. So I gave me f of x equals 2x plus 5, and it gave me g of x equals 3x minus 1. And this time I'm trying to find g of f to the minus 1. All right, now we're doing it method 1. The method 1 says we're going to find the f of minus 1 first. So let's write, let's go. So we have recognized that the g of f of minus 1 means g of f of minus 1. So we're doing the f of minus 1 first. How do f of minus 1? By putting minus 1 in the f function there. And so this becomes g of, and the f of minus 1 now is 2 times minus 1 plus 5. Because remember, we're putting the minus 1 there. That's how I get this. All right, f of minus 1. And then I work out what is in the bracket. So I get g of, this is minus 2 plus 5. Minus 2 plus 5 is 3. So I'm now just working out g of 3. And then g of 3 now means that I put 3 in the g function there. That's what g of 3 means, you know. 3 in the g function. So it becomes 3 times 3, where the x was, minus 1. 3 times 3 is 9. 9 minus 1 is 8. That's when I find it. inner function first, f to the minus 1, which worked out to be 3. All right. Or the other method now, or I could find g of, or the R method is, let's try to generate, find g of f of x first. In other words, find a composite function first. Remember, find a composite function. We're working with the f equals 2x plus 5 and the g equals 3x minus 1. And we're trying to form that composite function first, g of f of x. Now let's write also this equal to again. What does this mean up here? Let's write it up here. This means, remember this means, let's put it up here. Shall we up first? I'm going to use the blue. This means, remember, this means f into g. Remember that's what it means. This into this. That's what it means. F into g. Calculation, right? That's what it means. F into g, right? But remember, I know the inner one into the outer one. The inner one into the outer one. That's what it means. So put in f into g. We're going to put f into g now. It means that we're going to take all of the f that this is and bring it and put it into the g right here where the x is. Taking it there to form the composite function. All right. And when we do that, what do we get? What do we get? We get the 3 where the x was, we put 2x plus 5 minus 1. That's what we get. Because the x is replaced with the 2x plus 5. All right, and then we work this down now. So we get 3 2 is 6x, 3 5 is 15, 15 minus 1. All right, I wrote 5, 15 minus 1. All right, and then this becomes 6x plus 14. So now that I have my g of f of x, g of f of x, I can say, therefore, what did I want again? I wanted g of f to the minus 1. So I do not put the minus 1 in this. G of f of minus 1 becomes 6 times minus 1 plus 14. Now 6 times minus 1 is minus 6, you know. So it becomes minus 6 plus 14. Same as 40 minus 6. 40 minus 6 is 8. So again, you see, you get the same answer. Doing it either way. Again, I prefer this method. If they don't ask me to find this first, I'm doing it this way. All right, it's up to you which way you prefer. But basically, the remaining slides in the PowerPoint class is basically these examples. All right, so let's look at it just to confirm and look what the homework is going to be. All right, between now and tomorrow. Tomorrow can reinforce all of it. So see it here, it's the same thing. We'll find the g of 2 first and get the g of 5, and we got the 15. All right, and then in this way, I was finding the using the inner function first. All right, and then I got the 8, and then over the next example, I found a composite function. All right, found a composite function because remember the f of g means g into f. So I put the g into the f right there. That's how I get that. All right, and we're gone, and then we get that 15. And then now for the g to the minus 1, the other way around, when I want the g of f to get the 8, I put the f into the g. So I put the f now into the g. And that's how I get that. Right? And then you work it, you're gonna get 8. Alright, so that's what we just did on there. That's what I just wrote out for you. So we covered it. That's the homework, guys. So this is on the functions, in the functions handout. homework number 1. And the functions handout homework number 1. Let me show you what it's supposed to look like. Functions homework number 1. So let's see. See it here. I don't have it. Wait. Don't move. Let me show you that thing. Don't move, guys. Function homework number 1. I'm supposed to have it here. I don't have it here, so. All right, I don't have it here, so. But in your handout that I sent you, a handout that I sent you is homework number 1. Let me see something. Don't hang up. Let me see something. On this. Let me see something. Don't move. Homework. Oh, it might be in the handout. Yeah, man, it's in this file that I looked at. What am I talking about? The handout. Let's see. It's supposed to be in this. Let's see if it is in this. No, it's not in this, is it? No, it's not in this. I have to send another sheet. For those who are sent, I've only sent the thing there. Yes, I don't have it here. I need to send the persons who are sent some files this morning. Those who don't have the handout, I'll have to send you. I don't send you the notes. So I need to send you the homework as well. All right, it's a good thing I looked. So those who have the handout, those who went to the bookshop and got the handout, it is there. So it is classwork, variations, classwork. I've sent the ranking twice. All right, no problem. So yeah, so you need to get the homework as well. So I'll send it right after the class. Those who don't have the handout. The booklet, the handout booklet, you will have it in there. Those who have the booklet. Those who don't have the booklet, I'll have to send it. So I'll send the homework right after. Oh man, I have it, man. Functions, I have it here. Functions and teacher, man, I have it here, man. I have it. I've got it. I sent it. You have it. This is it. Download. Hold on, guys. Give me a second. Give me a second. When was doing this? Functions and variations. This is it, you know. Download. All right. All right. It may be a problem, but you're supposed to have it. Let me look at it and something. Don't move. I still wanted to see it, you know. All right. I still wanted to see it. All right. Tell you what I'm going to do so you can see. I'm gonna just pause the recording. I don't need this for the recording. Let's pause the recording so you can see it. So we're all on the same page. Let's pause the recording. All right. That is it for today. So we'll pick up back tomorrow. I think we'll do a good day's class today. Everybody's in attendance. Let me see. Practice. All right. All right. So. All right. So we'll meet up again tomorrow, guys. I think 3 o'clock is the same time. If there's gonna be a change, I'll let you know. All right. But that is the plan. 3 o'clock tomorrow. If not 3 o'clock, then 5 o'clock. But I'll definitely let you know before the class. Remember, anything you don't understand, let me know. Remember, my complaint today is that person not doing the work. You have to do the work. When I send your work to do, you need to do the work. All right. Can't do much without actually doing the work. All right, cool. So see you all tomorrow. Have a great rest of your day and start doing the questions right away. Nobody wait till tomorrow or to start or tonight. Just have a little free time, take a little break, just finish class, start the questions right away when the information is fresh. All right. I'm gonna post the video as soon as it is up. You can all have a chance to look at it and revise. All right. That's a very easy topic. So see you all. See you all tomorrow. Okay.
Bye-bye.
All right.
Yes.
Bye.
All right, sure. All right, sure.
Okay.
Bye, Dad.
All right, my princess. Bye.